Hello there, and welcome to Science for Sleep, the quiet little corner of the universe where curiosity slows down, science takes its time, and the vast mysteries of the cosmos are explored at a pace gentle enough to drift alongside your thoughts as they begin to soften toward rest. Tonight's journey begins not with something bright or dramatic, but with something strangely calm and almost invisible. We're going to talk about emptiness. Not the kind of emptiness you feel when the fridge is unexpectedly bare at midnight, and not the kind that appears when a meeting invitation suddenly disappears from your calendar. No, the emptiness we're visiting tonight lies far beyond our planet, far beyond our solar system, even beyond our galaxy. It's a place astronomers call the local void. Now that name might sound a little dramatic, like something from a science fiction novel, or a mysterious region marked on a galactic map with warning signs and ominous music playing quietly in the background. But in reality, it's something both simpler and stranger. The local void is a region of space close to our own cosmic neighbourhood that contains very few galaxies. In fact, compared to the busy regions of the universe where galaxies gather in enormous clusters and filaments, the local void is almost empty. Almost. But before we wander too far into this quiet cosmic region, I'd love to know something about you. Where in the world are you listening from tonight? Maybe you're in a city where the lights outside blur softly against the night sky. Maybe you're somewhere quieter, where a few stars peek through above rooftops or trees. And what time is it for you right now? Perhaps it's late evening, that comfortable hour when the day has finished asking things of you. Or maybe you're listening even later, when the world grows quieter and thoughts slow down. It feels fitting to ask that question tonight, because this story, in a strange way, is also about where we are. Not just on Earth, not just within the Milky Way galaxy, but within the much larger structure of the universe itself. The local void sits very close to our cosmic address, like an enormous empty valley next to a bustling city of galaxies. And if you find this journey relaxing, interesting, or simply a pleasant way to let your mind wander before sleep, I'd be quietly grateful if you gave the video a like, or perhaps subscribe to the channel. It helps this little sleepy science corner reach others who might enjoy a calm exploration of the universe before drifting off. Now then, let's settle in and begin. Most of us grow up with a mental picture of space that looks something like a giant dark ocean sprinkled with stars. If you imagine travelling far enough away from Earth, you might picture stars slowly thinning out, like lights fading along a distant highway. Eventually, you might expect that space becomes emptier and emptier until there's almost nothing left. But the real universe is organised in a far more interesting way. Galaxies, those enormous islands of stars containing billions or even trillions of suns, are not spread evenly through space. They gather together, they form groups, clusters, and long sprawling chains that stretch across unimaginable distances. If you could zoom out far enough to see the universe on its largest scales, it wouldn't look like scattered grains of sand at all. Instead, it would resemble something closer to a vast cosmic web. Imagine delicate threads of galaxies stretching across space, intersecting in bright knots where clusters gather. Between those threads lie enormous regions where very little exists at all. Astronomers call these places cosmic voids, and our story tonight focuses on one of those voids, one that sits remarkably close to us, the local void. Now here is where things start to become especially interesting. When people hear the word void, they often imagine an area where absolutely nothing exists. Total emptiness. A perfect vacuum with no stars, no galaxies, and no matter at all. But the universe rarely deals in perfect emptiness. Even the quietest cosmic regions contain something. A few lonely galaxies drifting slowly through vast darkness. Thin traces of gas. Invisible clouds of dark matter. So when astronomers describe the local void as empty, what they really mean is that it contains far fewer galaxies than expected. Picture standing on the edge of a busy city. Behind you, skyscrapers cluster together, streets glow with lights, and traffic moves steadily through intersections. But if you look out in one direction, the buildings suddenly stop. Instead of more city blocks, you see a vast open plain stretching far into the distance. That's roughly what our cosmic neighbourhood looks like. On one side, galaxies gather in dense structures known as filaments and clusters. On the other side lies an enormous underpopulated region of space, and that region begins surprisingly close to the Milky Way. In fact, astronomers believe that our galaxy sits right along the edge of the local void. We're not deep inside it, but we're certainly neighbours with it. Imagine living in a town built right at the border between a busy region and a vast empty landscape. Just beyond the last houses, the terrain opens into a huge quiet valley. Except in this case, the valley isn't a few miles across. It stretches tens of millions of light years. Even saying that number out loud feels a little unreal. A single light year, after all, is the distance light travels in 1 year, which works out to nearly 10 trillion kilometres. Multiply that by millions, and the scale quickly becomes difficult to picture. And yet the local void may span something on the order of 150 million light-years across. To give a gentle sense of that distance, imagine light leaving Earth tonight and travelling continuously through space. It would pass the moon in just over a second. It would reach the sun in about 8 minutes. It would cross the entire solar system in several hours. But to travel across the local void? That beam of light would keep moving for roughly 150 million years before reaching the other side. Now that's a long trip. The strange part is that astronomers didn't discover this enormous emptiness all at once. No telescope suddenly revealed a giant dark bubble labelled local void. Instead, the discovery emerged gradually as scientists began mapping the positions of nearby galaxies. Throughout the 20th century, astronomers improved their ability to measure distances to galaxies beyond the Milky Way. With each new observation, they added another point to a growing three-dimensional map of our cosmic neighbourhood. And something curious started to appear. In certain directions, galaxies were plentiful. Clusters gathered together, forming large structures like the Virgo cluster, which contains thousands of galaxies and sits about 55 million light-years away from us. But in other directions, the map looked strangely sparse. Astronomers would peer into those regions expecting to find more galaxies farther out, but instead they found very few. The deeper they looked, the emptier the region seemed. At first, this was a bit puzzling. Maybe the observations were incomplete. Maybe distant galaxies in that direction were simply harder to detect. But as the surveys improved, the pattern became clearer. There really was a large underpopulated region sitting right next to our galactic neighbourhood, the local void. One of the astronomers who studied this structure in detail was Brent Tully, a researcher who has spent decades mapping the distribution of galaxies around the Milky Way. His work helped reveal not only where galaxies are located, but how they move through space under the influence of gravity. And here's where things take another intriguing turn. It turns out that the local void doesn't just sit quietly beside us like a silent neighbour. Its presence actually influences the motion of nearby galaxies. Gravity, as you probably know, pulls things together. Massive clusters of galaxies tug on surrounding objects, drawing them inward over billions of years. But emptiness can create an effect of its own. If one side of your cosmic neighbourhood is densely packed with galaxies, and the other side is relatively empty, the gravitational pull will be stronger toward the crowded side. That means galaxies near the edge of a void tend to drift away from the emptiness, and toward regions filled with matter. And when astronomers measured the motion of galaxies around the local void, they noticed exactly that pattern. The Milky Way itself, along with neighbouring galaxies in our local group, appears to be slowly moving away from the void. Not quickly, not dramatically, but steadily. It's almost as if the local void is gently pushing us away, not by exerting force, but by lacking it. That idea can feel a bit strange at first. We're used to thinking of motion being caused by something present, like a gravitational pull or a burst of energy. But sometimes the absence of matter can shape motion just as effectively as its presence. Picture a large crowd leaving a stadium through several exits. If one exit suddenly opens into a huge empty field, while the others lead into busy streets, people will naturally drift toward the areas with clearer pathways. In a similar way, galaxies flow through the universe along paths shaped by both crowded regions and enormous voids, and the local void happens to be one of the nearest examples of such an empty region. For astronomers trying to understand the structure of the universe, that makes it an especially fascinating place to study. Because the universe, it turns out, is not built like a uniform fog of galaxies. Instead, it resembles a complex landscape of dense regions, sprawling filaments, and vast empty cavities. The local void is one of those cavities, but just how empty is it really? That question turns out to be more complicated than it might first appear. Measuring emptiness, after all, is not as straightforward as measuring something solid like a planet or a star. You can't simply place a cosmic ruler across a void and read off the number. Instead, astronomers must build detailed maps of galaxy positions and distances, gradually revealing where matter gathers and where it thins out. And as those maps improved over the years, the picture of the local void became clearer. Yet even today, scientists are still refining their understanding of its true size and shape. Some regions appear nearly devoid of galaxies for tens of millions of light years. Other parts contain a few scattered galaxies drifting quietly through the darkness. So the local void isn't a perfectly smooth bubble. It's more like a vast underpopulated landscape, with occasional lonely islands of stars. And those islands raise an interesting question of their own. What is it like for a galaxy to live inside a cosmic void? That's something astronomers have been studying carefully, because galaxies inside voids tend to behave a little differently from those packed into crowded clusters. With fewer neighbouring galaxies nearby, they experience fewer collisions and gravitational disturbances. Life inside a void, cosmically speaking, can be rather quiet. But before we explore those lonely galaxies and the surprising environments they inhabit, it helps to step back and look at the bigger picture of how galaxies are arranged across the universe. Because once you begin to map galaxies on truly enormous scales, an unexpected pattern starts to emerge. One that makes the local void feel less like a strange anomaly, and more like a natural part of the universe's architecture. And that pattern begins with something astronomers often call the cosmic web, a structure so vast that even entire galaxy clusters become tiny threads within it. So as we continue drifting through tonight's story, we'll gradually widen our view of the universe, moving from our immediate galactic neighbourhood outward into the enormous structures that shape everything around us. And somewhere along the way, the local void will begin to make a little more sense. If you step outside on a clear night and look up at the sky, the first thing you might notice is how peaceful everything appears. A handful of bright stars, perhaps a faint band of milky light stretching across the darkness, and beyond that a quiet black sky that seems almost empty. It can feel as if we are floating alone in a calm, silent ocean of space. But appearances can be a little misleading. That tranquil sky hides an enormous and surprisingly busy neighbourhood, one that extends far beyond the stars visible to our eyes. To understand the local void, the strange empty region we began discussing earlier, it helps to first understand exactly where we live in the universe. And when astronomers talk about where we are, they don't just mean our street or city or even our planet. They mean our full cosmic address, a set of nested neighbourhoods stretching outward from Earth into some of the largest structures known to science. So let's start close to home and gradually widen the view. Right now, wherever you happen to be listening from, you're sitting on a planet called Earth. Earth is a fairly comfortable place as planets go. It has oceans, weather, mountains, forests, and the occasional late-night cup of tea or coffee. It also has something that's easy to overlook when we're busy with daily life: motion. Earth is constantly moving through space. At this very moment, the planet beneath you is rotating once every 24 hours, giving us the cycle of day and night. At the same time, Earth is orbiting the Sun at a speed of roughly 30 kilometers per second, That means every second we travel about the length of several city blocks through space without noticing it at all. The Sun itself sits at the centre of our solar system, a glowing sphere of hot gas containing more than 99% of all the mass in the system. Orbiting around it are 8 planets, countless asteroids, icy comets, and a wide halo of distant objects far beyond the orbit of Neptune. This entire region, stretching for billions of kilometres in every direction, is what we call the solar system. But even the solar system, vast as it seems on a human scale, is just a tiny island within something much larger. The Sun is one of hundreds of billions of stars belonging to a galaxy known as the Milky Way. If you've ever seen photographs of spiral galaxies taken by powerful telescopes, you'll have a good idea of what the Milky Way probably looks like from the outside. It's a broad rotating disk of stars, gas and dust, with graceful spiral arms winding outward from a bright central bulge. Those spiral arms contain many of the younger stars in the galaxy, along with enormous clouds of gas where new stars continue to form. Our solar system sits inside one of those spiral arms, about 27,000 light-years away from the galactic centre. That location places us roughly halfway between the centre and the outer edge of the galaxy. Not too crowded, not too empty, something like living in the suburbs of a very large city. And the Milky Way itself is enormous. From one side to the other, the galaxy spans about 100,000 light-years. That means if a beam of light started at one edge and travelled continuously across the galaxy, it would take 100,000 years to reach the opposite side. Inside that vast structure live somewhere between 100 and 400 billion stars. Many of those stars likely have their own planets, some perhaps similar to Earth, others very different. The night sky we see from our planet is only a tiny glimpse of this enormous stellar city. Yet even the Milky Way is not alone. Galaxies, like stars, tend to gather together in groups. Our galaxy belongs to a small collection of galaxies known as the local group. The name might sound modest, but the local group still spans about 10 million light-years across and contains more than 50 known galaxies. 2 of those galaxies dominate the group. One is the Milky Way, the other is the Andromeda Galaxy, a slightly larger spiral galaxy located about 2.5 million light-years away. If you could see Andromeda with your naked eyes under very dark skies, it would appear as a faint oval smudge in the constellation of Andromeda. What you'd actually be looking at is a vast galaxy containing perhaps 1 trillion stars. The Milky Way and Andromeda are slowly drifting toward one another through space. Over the next 4 to 5 billion years, the 2 galaxies will eventually collide and merge, forming a much larger galaxy. But there's no need to worry about stars crashing into each other during that event. Even in galaxies, space between stars is so large that direct collisions are extremely rare. Besides these 2 giants, the local group also contains dozens of smaller galaxies. Some are dwarf galaxies with only a few billion stars, while others are tiny collections of stars containing only a few million. Several of these small galaxies orbit the Milky Way itself, much like moons orbit a planet. If we zoomed out far enough to see the entire local group from a distance, we'd observe a loose gathering of galaxies drifting through space together, bound by their mutual gravity. And the local group, as it turns out, is only the next layer of the cosmic neighbourhood. Beyond it lies an even larger structure called the Virgo supercluster. This immense region contains tens of thousands of galaxies arranged into numerous clusters and groups. At its centre sits the Virgo cluster, a dense gathering of over 1,000 galaxies located roughly 55 million light-years away. For many years, astronomers thought the Virgo supercluster represented one of the largest structures in the universe. But as observations improved, scientists realized that the Virgo supercluster itself is part of something even larger. In 2014, astronomers introduced a new name for the enormous region of space that contains our galaxy and many surrounding clusters. They called it Laniakea. The name comes from the Hawaiian language and means immeasurable heaven, which feels appropriate for a structure containing more than 100,000 galaxies spread across roughly 500 million light-years. Within Laniakea, galaxies are not scattered randomly. Instead, they flow slowly along enormous gravitational pathways toward dense regions of matter. Astronomers sometimes compare these motions to rivers flowing across a landscape, with galaxies drifting along cosmic currents toward massive clusters. All of this motion happens incredibly slowly on human timescales. A galaxy might take billions of years to complete one such journey. Yet when scientists map the velocities of galaxies in 3 dimensions, they can see these patterns emerging. It's like watching an extremely slow dance taking place across the universe. Now here is where the local void begins to fit into the story. When astronomers mapped the motion of galaxies near the Milky Way, they noticed something intriguing. Our galaxy and its neighbours weren't simply drifting toward dense clusters like Virgo. They were also moving away from a large region where very few galaxies existed. That region was the local void. Imagine standing in a gently sloping valley surrounded by hills. Water will naturally flow downhill toward the lowest points, but it will also move away from higher ground. In a similar way, galaxies tend to drift away from underpopulated regions where gravity is weaker. So when scientists charted the motion of nearby galaxies, they realized that our local cosmic neighborhood sits right along the edge of an enormous empty region. One side of our neighborhood is rich with galaxies and clusters. The other side opens into the quiet expanse of the local void. The discovery was both surprising and fascinating, because it revealed that our place in the universe isn't just defined by what surrounds us, but also by what doesn't. In other words, our cosmic neighborhood is shaped not only by galaxies and clusters, but also by the enormous empty spaces between them. Those empty spaces are far larger than the dense regions. In fact, most of the universe by volume is made up of cosmic voids. The galaxies we see, impressive as they are, actually trace the edges of these enormous cavities like lights outlining the borders of vast bubbles. The filaments and clusters form the skeleton of the cosmic web, while the voids occupy the enormous spaces in between. And the local void is simply one example of such a bubble, but it's a particularly interesting one because of its proximity to us. Astronomically speaking, it's right next door. If you could travel millions of light years beyond the Milky Way and look back toward our region of space, you would see our galaxy sitting along the boundary between a busy network of galaxies and a huge dark region where only a few scattered galaxies drift through the emptiness. That contrast between crowded and empty space is one of the defining features of the large-scale universe. It's also one of the most beautiful discoveries modern astronomy has revealed. Because once scientists began mapping galaxies on very large scales, they realized that the universe doesn't resemble a uniform cloud at all. Instead, it looks something like a vast foam or sponge, with enormous bubbles separated by thin walls and filaments. And inside those bubbles lie the cosmic voids. Some are small by cosmic standards, perhaps 20 or 30 million light-years across. Others are enormous, spanning hundreds of millions of light-years. The local void falls somewhere in between, though its exact boundaries are still being studied. Astronomers continue to refine their maps of nearby galaxies, and with each new survey the shape of the local void becomes a little clearer. Yet the more scientists study these enormous empty regions, the more questions arise. Why did voids form in the first place? How empty are they really? And how do these vast cavities influence the motion of galaxies around them? If you could somehow travel far beyond the Milky Way and keep going for millions of light years, you might expect the universe to gradually look simpler. Perhaps galaxies would thin out evenly, becoming more scattered the farther you travelled. That was actually the picture many astronomers imagined for a long time. The universe, in this early view, was thought to be more or less uniform when seen on very large scales. Galaxies might gather in small groups here and there, but overall the distribution would smooth out into something like a gentle cosmic fog. But as telescopes improved and astronomers began mapping the positions of galaxies across vast distances, that simple picture slowly started to fall apart. The first hints appeared when scientists began conducting large galaxy surveys. Instead of studying individual galaxies one by one, researchers started collecting enormous catalogues containing thousands and eventually millions of galaxies. Each galaxy's position in the sky was measured carefully, and its distance from Earth was estimated using a clever technique involving the stretching of light. You might remember that the universe is expanding. As galaxies move away from us through that expansion, the light they emit becomes stretched toward longer wavelengths. Astronomers call this effect redshift, because the light shifts slightly toward the red end of the spectrum. By measuring how much a galaxy's light has been stretched, scientists can estimate how far away it is. With that information, they can place the galaxy into a three-dimensional map of the universe. Now imagine plotting those positions one by one. At first, the map might look like a loose scatter of points, each representing a distant galaxy. But as more and more galaxies are added, patterns begin to emerge. And the pattern astronomers discovered was not at all what they expected. Instead of forming a smooth distribution, galaxies seem to arrange themselves into enormous filaments, walls, and clusters, leaving behind vast, empty regions between them. The overall structure looked surprisingly similar to foam. Picture a sink full of soap bubbles. The bubbles themselves create large hollow spaces, while thin walls of soap form the boundaries between them. In the cosmic version of this structure, the bubbles are the voids, and the thin walls are where galaxies gather. Astronomers eventually began referring to this arrangement as the cosmic web. The name fits remarkably well, because when scientists map the universe across hundreds of millions of light years, the distribution of galaxies resembles a delicate three-dimensional network. Long threads of galaxies stretch across space, intersecting at dense knots where galaxy clusters reside. Between those threads lie enormous empty cavities. Some of these voids are tens of millions of light years wide. Others are far larger. And somewhere along the boundary of one of those enormous cavities sits our galaxy. The local void we introduced earlier is just one bubble within this cosmic foam. But before astronomers could fully understand voids, they first had to uncover the full structure of the web itself. One of the earliest glimpses came in the late 20th century, with a famous project known as the CFA Redshift Survey, conducted by astronomers at the Harvard-Smithsonian Center for Astrophysics. The goal of the survey was ambitious but straightforward: measure the redshifts of thousands of galaxies and plot their positions in 3 dimensions. When the first slices of that map were drawn, the results stunned researchers. Instead of a random scattering of galaxies, the map showed a pattern resembling lace or sponge. Galaxies formed long chains stretching across the chart, with huge empty regions in between. One particularly striking feature appeared as an enormous arc of galaxies stretching across more than 500 million light-years. Astronomers called it the Great Wall. For comparison, the Milky Way itself spans about 100,000 light-years. That means the Great Wall is roughly 5,000 times larger than our entire galaxy. Discoveries like this changed the way scientists thought about the universe. Instead of being a smooth sea of galaxies, the cosmos turned out to be structured in layers, with enormous features spanning unimaginable distances. The cosmic web became one of the defining discoveries of modern cosmology. But how did such a structure form? To answer that question, astronomers had to look far back in time, nearly to the beginning of the universe itself. About 13.8 billion years ago, the universe began in an event we call the Big Bang. In the earliest moments after that event, the universe was extremely hot and dense. Matter existed mostly as a glowing plasma of particles and radiation. As the universe expanded and cooled, tiny fluctuations in density began to appear. Some regions were ever so slightly denser than others. At first, those differences were incredibly small. Imagine a perfectly smooth surface with tiny ripples only a few parts in 100,000. That was roughly the level of variation in the early universe. But gravity is patient. Over millions and billions of years, those slightly denser regions began pulling in more matter. As they grew, their gravitational pull strengthened, drawing in even more material from the surrounding space. Gradually, the densest areas collapsed into the first galaxies. Meanwhile, other regions lost matter as it flowed toward the growing structures. Those areas became increasingly empty. This process slowly sculpted the universe into the pattern we see today. Matter collected into filaments and clusters, while vast regions between them were drained of material. The result was the cosmic web. Computer simulations of the universe show this process beautifully. When scientists simulate billions of particles under the influence of gravity over cosmic time, the particles naturally organize themselves into a network that looks remarkably like the observed distribution of galaxies. Thin filaments stretch across space, connecting dense clusters. Between them lie enormous voids. The resemblance between simulations and real observations is one of the strongest confirmations that our understanding of cosmic structure is on the right track. There's another key ingredient in this story as well. Most of the matter shaping the cosmic web is not visible. Astronomers call it dark matter. Dark matter does not emit light, absorb light, or reflect light in any measurable way. It interacts with ordinary matter mainly through gravity. Although we cannot see it directly, its presence becomes obvious when we observe how galaxies move and how gravitational forces behave on large scales. Current estimates suggest that dark matter makes up about 85% of all matter in the universe. In other words, the visible galaxies we see are only a small fraction of the total cosmic structure. The rest is an invisible framework of dark matter forming the underlying skeleton of the cosmic web. Galaxies tend to form where dark matter has gathered into dense regions. That's why the distribution of galaxies traces the web so clearly. In this sense, the universe can be imagined as a vast invisible scaffold made of dark matter, with galaxies lighting up the densest intersections like glowing lanterns. Once astronomers began mapping this structure in detail, they realized that the largest features in the universe are truly enormous. Filaments can stretch for hundreds of millions of light years. Clusters of galaxies can contain thousands of individual galaxies bound together by gravity. And voids can span regions so large that a beam of light would take hundreds of millions of years to cross them. The local void sits within this enormous network, just one bubble in the cosmic foam. But it happens to be a particularly interesting one because of how close it lies to our own galaxy. Most cosmic voids are discovered far away, visible only through deep surveys of distant galaxies. The local void, by contrast, occupies part of our immediate cosmic neighbourhood. And that proximity allows astronomers to study it in greater detail than many other voids. The challenge, however, is that mapping the region around the Milky Way is not as easy as it might sound. Our galaxy contains vast clouds of gas and dust that block our view in certain directions. When astronomers try to observe distant galaxies behind the dense plane of the Milky Way, much of their light becomes obscured. This region of the sky is sometimes called the zone of avoidance, because early galaxy surveys had difficulty observing through it. Unfortunately, part of the local void lies behind that dusty curtain. That means astronomers must use specialized techniques and wavelengths of light that can penetrate the dust in order to see what lies beyond. Over time, improved infrared and radio observations have gradually revealed more galaxies hiding behind the Milky Way's veil. With each new discovery, the map of our cosmic neighbourhood becomes more complete, and as that map fills in, the outline of the local void becomes clearer. Yet even with these advances, scientists are still refining the boundaries of the void. Some regions that once appeared completely empty have turned out to contain a few faint galaxies. Others remain remarkably barren. So the local void is not a perfectly smooth bubble carved out of space. It's more like a vast underpopulated territory with scattered islands of matter. That raises another interesting question. If galaxies tend to form along filaments and clusters, what happens to the rare galaxies that form inside voids? How do they evolve when they have almost no neighbours nearby? Those lonely galaxies turn out to be fascinating objects in their own right. Without frequent interactions with other galaxies, They often follow very different evolutionary paths compared to galaxies in crowded clusters. Studying them offers a unique window into how galaxies grow and change when left mostly undisturbed, and in the quiet depths of the local void, astronomers have found a few such galaxies drifting through the darkness, living out their cosmic lives far from the busy regions of the universe. But before we explore those solitary systems, it helps to focus more closely on the void itself. Because the local void is not just another empty region among many, its position right next to our galactic neighbourhood makes it one of the most intriguing structures in the nearby universe. And the story of how astronomers first realised it was there begins with a surprisingly simple question. When scientists started mapping galaxies around the Milky Way, why did they find so few in one particular direction? For most of the 20th century, astronomers assumed that the universe on its larger scales was fairly smooth. Not perfectly uniform, of course. Galaxies clearly gathered in clusters, and some regions contained more galaxies than others. But if you zoomed out far enough, scientists expected the overall picture to resemble something like a gentle mist of galaxies spread evenly through space. It was a reasonable assumption. After all, the early observations of galaxies were limited. Telescopes could only see so far, and the number of known galaxies was relatively small compared with today's enormous surveys. When astronomers plotted the locations of those early discoveries, the distribution did not reveal any obvious grand design. But as observational techniques improved and astronomers began collecting much larger data sets, something unusual started to appear. Certain regions of space looked empty. At first the pattern was subtle. A handful of astronomers noticed that in some directions galaxies seemed strangely scarce. Researchers would examine photographs of the sky and see clusters of galaxies gathered together in one area, yet in the neighbouring region there would be very few. The simplest explanation was that those areas simply had not been observed carefully enough. Telescopes at the time had limitations, and faint galaxies could easily be missed. So astronomers continued surveying the sky. Throughout the 1960s and 1970s, the number of known galaxies grew rapidly. Improved photographic plates allowed telescopes to capture deeper images of space. Radio telescopes began detecting galaxies hidden behind clouds of dust. New instruments measured galaxy distances more accurately than ever before. With each new survey, astronomers added thousands more points to their cosmic maps, and slowly the empty regions became harder to ignore. When researchers plotted galaxies in 3 dimensions using redshift measurements, they began to see enormous gaps in the data. These gaps were not small. Some appeared to span tens of millions of light years. The first reaction was skepticism. Astronomers are naturally cautious when a discovery challenges long-held assumptions. Empty regions that large seemed almost unbelievable. Perhaps the surveys were incomplete. Perhaps the galaxies were simply too faint to detect. But as independent teams conducted their own surveys and compared results, the same pattern kept appearing. Large regions of space contained far fewer galaxies than expected. Eventually, astronomers gave these regions a name. They called them cosmic voids. One of the earliest and most influential discoveries came in 1981, when astronomers Robert Kirshner, Augustus Oehmler, Paul Schechter, and Stephen Schechtman identified a particularly dramatic example. They were studying galaxies in the direction of the constellation Boötes when they noticed something remarkable. There appeared to be a gigantic region almost completely devoid of galaxies. This structure, later named the Boötes Void, spanned roughly 330 million light-years across. To appreciate how enormous that is, it helps to compare it with familiar cosmic scales. The Milky Way galaxy is about 100,000 light-years wide. That means the Boötes Void could fit thousands of galaxies like ours across its diameter. Yet inside that enormous volume, astronomers found only a handful of galaxies. The discovery of the Boötes Void forced scientists to rethink their understanding of cosmic structure. If such a vast empty region existed, then the universe clearly was not smooth at all. Instead, galaxies seemed to cluster together along large structures, leaving enormous gaps between them. As more galaxy surveys were completed, researchers began finding additional voids scattered throughout the universe. Some were smaller, perhaps 20 or 30 million light-years across. Others were enormous. What became clear was that voids were not rare anomalies. They were a fundamental part of the universe's architecture. In fact, when astronomers estimated the total volume occupied by these regions, they realized something surprising. Most of the universe, by volume, consists of voids. The galaxies, clusters, and filaments that we often think of as filling space actually occupy only a small fraction of the total cosmic volume. The vast majority of space lies inside these enormous underdense regions. If you could step far outside the observable universe and look back at it from a great distance, the distribution of matter might resemble something like a sponge or foam. Thin walls of galaxies would outline huge bubbles of emptiness. Each bubble would represent a cosmic void. This new picture of the universe was both beautiful and puzzling. It suggested that gravity had sculpted matter into an intricate network over billions of years. But the exact process that produced such enormous voids was not immediately obvious. To understand how voids form, scientists had to return to the early universe. Shortly after the Big Bang, matter was distributed almost uniformly throughout space. Tiny variations in density existed, but they were extremely small. Some regions contained slightly more matter than average, while others contained slightly less. Over time, gravity amplified those differences. The slightly denser regions pulled in additional matter, gradually forming the seeds of galaxies and clusters. Meanwhile, the slightly underdense regions lost matter as it flowed toward the denser areas. As billions of years passed, the dense regions grew denser, while the underdense regions became emptier. Eventually, enormous cavities emerged between the growing structures. Those cavities became the cosmic voids we observe today. Computer simulations of the universe have shown this process quite clearly. When scientists simulate billions of particles interacting through gravity, the particles naturally organize into a web-like structure with voids in between. The resemblance between these simulations and the real distribution of galaxies is striking. It suggests that the large-scale structure of the universe arises naturally from simple physical laws operating over immense spans of time. Yet the discovery of voids raised another intriguing question. What exactly exists inside them? At first, astronomers assumed that voids might be completely empty, but as telescopes became more sensitive, researchers began detecting occasional galaxies inside these regions. These galaxies are extremely isolated. Unlike galaxies in dense clusters, which frequently interact and sometimes collide with one another, void galaxies live in relative solitude. Their nearest neighbours may be tens of millions of light-years away. That isolation can have interesting consequences. Galaxies inside voids often evolve differently from those in crowded environments. Without frequent gravitational disturbances, their structures can remain relatively undisturbed for billions of years. Some void galaxies appear unusually rich in gas, suggesting that they have experienced fewer starburst events triggered by interactions with other galaxies. Others are small dwarf galaxies that formed quietly in regions where matter density was just barely sufficient for galaxy formation. Studying these galaxies helps astronomers understand how environment shapes the evolution of cosmic structures. Yet even more fascinating than the galaxies inside voids is the influence that voids exert on the galaxies around them. At first glance, emptiness might seem passive. After all, if a region contains very little matter, it might seem as though it would simply sit there without affecting its surroundings. But in reality, voids play an important role in shaping the motion of galaxies. Because voids contain less mass, their gravitational pull is weaker than that of surrounding regions filled with matter. Galaxies near the edges of a void tend to drift away from it, gradually migrating toward denser structures. Over billions of years, this effect helps enlarge the void even further. Matter flows outward from the empty region, accumulating along its boundaries. The result is a kind of cosmic expansion, occurring inside the void itself. While the universe as a whole is expanding everywhere, voids expand slightly faster because they contain less gravitational resistance. In this way, voids grow larger as the universe evolves, and that process continues even today. When astronomers began examining the motion of galaxies near our own cosmic neighbourhood, they noticed evidence of exactly this effect. Certain galaxies appeared to be moving away from a large underdense region nearby. That region, as it turned out, was the local void. Unlike the Butter's void, which lies hundreds of millions of light years away, the local void sits remarkably close to the Milky Way. In fact, our galaxy appears to lie right along its edge. This proximity makes the local void one of the most intriguing structures in the nearby universe. It also makes it more difficult to study, because parts of it lie behind the dense plane of the Milky Way, where dust obscures distant galaxies. For decades, astronomers struggled to map this region accurately. Observations in visible light were often blocked by interstellar dust, hiding galaxies that might lie beyond. Gradually, however, new techniques helped fill in the gaps. Infrared telescopes could see through much of the dust that blocks visible light. Radio telescopes detected hydrogen gas in distant galaxies even when their starlight was hidden. With these tools, astronomers began uncovering more details about the structure surrounding our galaxy, and what they found confirmed that a large void truly does exist beside our cosmic neighbourhood. The local void may not be quite as large as the Butter's void, but it still spans tens or possibly hundreds of millions of light years. Even more intriguingly, its influence appears to affect the motion of the Milky Way itself. Our galaxy, along with others in the local group, is not only moving toward massive clusters like Virgo, it is also drifting away from the local void, as though the emptiness beside us is gently nudging our galaxy outward. This subtle motion is one of the many clues astronomers use to map the distribution of matter in our region of the universe. Yet the full size and shape of the local void remain topics of ongoing research. Because parts of it lie behind the dense clouds of our own galaxy, astronomers continue to search for faint galaxies hidden within that region. With each new observation, the map becomes a little clearer. And as that map improves, scientists gain a better understanding of just how large the local void might truly be. Because once astronomers accepted that cosmic voids exist, the next natural question became a simple one. Where exactly are they? Once astronomers had accepted that enormous empty regions exist throughout the universe, the next challenge became figuring out exactly where those voids were located. Discovering that voids exist is one thing. Mapping them precisely is another matter entirely. After all, it's not always easy to measure something defined mostly by the absence of objects. Galaxies, at least, are easy to spot. They glow with billions of stars, sometimes surrounded by clouds of gas and dust that shine in many wavelengths of light. Telescopes can detect them from vast distances, but a void does not glow. It does not emit radiation. It does not stand out as a bright feature in the sky. Instead, a void reveals itself only through what is missing. Astronomers detect these regions by carefully plotting the locations of galaxies and noticing where the map becomes strangely sparse. If a large section of space contains far fewer galaxies than expected, that region begins to look suspiciously like a void. Over time, as galaxy surveys expanded and maps of the nearby universe became more detailed, astronomers noticed that one particular empty region seemed to lie unusually close to our own galaxy. This region would eventually become known as the local void. The name itself is simple and descriptive. Local does not mean close in the everyday sense, of course. In cosmic terms, even nearby structures are separated by tens of millions of light years, but compared with many other voids scattered throughout the observable universe, this one sits right in our cosmic neighbourhood. The story of how scientists first recognized the local void is a quiet example of how astronomy often works. There was no single dramatic announcement, no moment when a telescope suddenly revealed a giant empty bubble sitting beside the Milky Way. Instead, the discovery emerged gradually as astronomers pieced together the positions and motions of nearby galaxies. During the late 20th century, researchers began conducting increasingly detailed surveys of galaxies surrounding the Milky Way. They measured redshifts, calculated distances, and mapped the three-dimensional structure of the nearby universe as carefully as possible. One of the scientists who contributed significantly to this effort was Brent Tully, an astronomer who spent decades studying the motions of galaxies in our local cosmic environment. His work focused on understanding how galaxies move through space under the influence of gravity. At first glance, the motion of galaxies might seem random. After all, the universe is enormous, and galaxies are separated by vast distances. But gravity links everything together. Every galaxy experiences the gravitational pull of nearby structures, from neighbouring galaxies to massive clusters containing thousands of galaxies. By measuring how galaxies move relative to one another, astronomers can learn a great deal about the distribution of matter in the universe. In particular, galaxy motions can reveal the presence of both dense regions and empty ones. When Tully and other astronomers began analysing the velocities of nearby galaxies, they noticed something curious. Many galaxies near the Milky Way appeared to be moving in a similar direction. Part of that motion made sense. Our local group of galaxies is slowly drifting toward the Virgo cluster, a massive gathering of galaxies about 55 million light-years away. The gravitational pull of Virgo influences the motion of many nearby galaxies, but the observed motions contained another component that seemed harder to explain. Galaxies near us appeared to be moving away from a region of space where relatively few galaxies existed. In other words, something about that region seemed to be pushing galaxies outward. Of course, nothing was actually pushing them. In physics, motion like this usually arises from gravitational differences rather than forces pushing objects directly. Imagine standing on a gently sloped hill. If you release a ball, it rolls downhill not because something pushes it, but because gravity pulls it toward lower elevations. In a similar way, galaxies move through space in response to the distribution of mass around them. Regions filled with galaxies and dark matter exert strong gravitational pulls. Regions with very little matter exert much weaker pulls. If a galaxy sits near the boundary between those two environments, it will tend to drift toward the denser side. That realization helped astronomers interpret the unusual motions they were observing. The galaxies in our neighbourhood were not simply being pulled toward massive clusters like Virgo. They were also drifting away from a large underdense region nearby. That underdense region turned out to be the local void. Once researchers began examining galaxy maps more closely, they noticed that the distribution of galaxies in one direction from the Milky Way looked unusually sparse. Compared with other parts of the sky, there were far fewer galaxies in that region. This absence was not subtle. Where astronomers expected to find a steady scattering of galaxies stretching into the distance, they instead found a vast expanse containing very few. It was as though someone had erased a large portion of the cosmic map. But confirming the existence of the local void was not entirely straightforward. Part of the challenge came from our own galaxy. The Milky Way contains enormous clouds of gas and dust that obscure our view in certain directions. When astronomers look toward the dense plane of the galaxy, the dust blocks light from distant objects behind it. This region of the sky is sometimes called the zone of avoidance, because early galaxy surveys avoided it due to the difficulty of seeing through the dust. Unfortunately, a significant portion of the local void lies behind this obscured region. That means astronomers cannot simply point an optical telescope in that direction and easily detect all the galaxies that might exist there. For many years, this made the structure of the local void somewhat uncertain. Perhaps the region only appeared empty because galaxies were hidden behind the Milky Way's dusty veil. To investigate this possibility, astronomers began using telescopes that observe wavelengths of light capable of penetrating dust. Infrared telescopes can detect the glow of stars even through dense clouds of interstellar dust. Radio telescopes can detect emissions from hydrogen gas within galaxies that would otherwise remain hidden. Using these techniques, researchers slowly began uncovering galaxies behind the plane of the Milky Way. And as those hidden galaxies were added to cosmic maps, the outline of the local void became clearer. Even after accounting for galaxies hidden behind dust, the region still appeared remarkably underpopulated. In other words, the emptiness was real. Today, astronomers believe that the local void begins just beyond the edge of our immediate cosmic neighbourhood and stretches outward for tens of millions of light years. Some estimates suggest it could span roughly 150 million light years across, though its exact shape is somewhat irregular. Voids rarely form perfect spheres. Instead, they resemble lumpy bubbles that merge and distort over time as matter flows along the filaments of the cosmic web. The local void appears to be one such irregular cavity within that web, and our galaxy sits right along its boundary. That location is particularly interesting because it allows astronomers to observe how the presence of a void affects nearby galaxies. When scientists analyse the motion of galaxies near the Milky Way, they see evidence that our local group is slowly moving away from the local void. This motion is not dramatic. The speed involved is only a few hundred kilometers per second, which may sound fast but is relatively gentle on cosmic scales. Still, over billions of years, that motion becomes significant. The local void is gradually expanding as matter flows away from its interior and accumulates along its edges. In a sense, the void is growing. This behavior is predicted by cosmological models. Because voids contain less matter, their gravitational pull is weaker. As the universe expands, matter tends to drift away from these underdense regions toward denser structures. The process slowly enlarges the void while simultaneously strengthening the filaments and clusters surrounding it. One way to visualize this process is to imagine a loaf of raisin bread rising in an oven. As the dough expands, the raisins move farther apart from one another, but if some regions of the dough contain fewer raisins to begin with, those areas become even emptier as the bread expands. In the cosmic version of this scenario, galaxies are the raisins, and the expanding universe stretches the space between them. Regions with few galaxies become larger voids over time. The local void is a particularly nearby example of this process. Despite its proximity, however, the void remains somewhat mysterious. Astronomers continue to search for faint galaxies within it, hoping to determine exactly how empty it truly is. Some surveys have detected a handful of galaxies drifting quietly through the void, but their numbers are extremely small compared with typical cosmic regions. These galaxies often live in extreme isolation, separated from their nearest neighbours by tens of millions of light years. Studying them offers valuable clues about how galaxies evolve when they grow in near solitude. When astronomers first began mapping the nearby universe in detail, they were not searching for a giant empty region beside the Milky Way. Their goal was much simpler. They wanted to understand where galaxies were located and how they moved through space. At the time, the idea of a vast cosmic void sitting next to our galactic neighbourhood had not yet entered the conversation. Most scientists expected the nearby universe to contain a fairly balanced distribution of galaxies. Some regions would certainly be more crowded than others, but overall the pattern should look reasonably continuous when plotted across large distances. If you kept mapping galaxies farther and farther from Earth, the points on the map should gradually fill in. Instead, something unexpected began to appear. Certain directions looked strangely quiet. When astronomers observed galaxies surrounding the Milky Way, they noticed that some regions of space contained clusters and groups that were easy to identify. These areas were rich with galaxies. Large spirals, small dwarfs, and irregular galaxies all appeared scattered across the sky, often bound together in loose gravitational families. But in another direction the map looked sparse. At first, this did not seem especially unusual. After all, galaxy surveys were still incomplete, and telescopes at the time could only detect galaxies above certain brightness thresholds. it was entirely possible that many faint galaxies simply had not been discovered yet, so astronomers continued collecting data. Through the 1970s and 1980s, researchers improved their techniques for measuring galaxy distances. Instead of relying solely on photographic images, they began using spectroscopy to measure redshift more precisely. This allowed them to build three-dimensional maps of galaxy positions, revealing not only where galaxies appeared on the sky, but also how far away they were. As these maps grew more detailed, patterns began to emerge. In one region of the nearby universe, the density of galaxies dropped dramatically. This was not just a small gap between clusters. The region seemed to extend across tens of millions of light-years, with surprisingly few galaxies inside it. Astronomers began referring to this area informally as an underdense region. In scientific terms, that means a place where the density of matter is lower than the cosmic average. But the real puzzle was determining whether the emptiness was genuine. There were several reasons to be cautious. The Milky Way itself complicates observations in certain directions. Our galaxy contains enormous clouds of dust and gas concentrated along its central plane. When astronomers try to observe distant galaxies through this region, much of the incoming light becomes absorbed or scattered. The result is a band across the sky where distant galaxies become difficult to detect. This region is often called the zone of avoidance because early galaxy surveys avoided it almost entirely. Observers simply could not see through the dust well enough to map galaxies hidden behind it. Unfortunately, part of the suspected empty region lay close to this obscured area. That raised an important question. Was the region truly empty, or were galaxies simply hidden behind the Milky Way's dusty curtain? To answer that question, astronomers had to gather evidence from multiple directions. They needed to examine the distribution of galaxies surrounding the suspected void, and see whether the emptiness extended beyond the dusty region. As more galaxy surveys were completed, the pattern persisted. The sparse region appeared not only behind the plane of the Milky Way, but also in nearby directions where dust was not a major obstacle. Even when astronomers looked deeper into space using more sensitive instruments, they still found relatively few galaxies there. The emptiness seemed genuine. One of the most important pieces of evidence came from studies of galaxy motion. As researchers measured the velocities of galaxies in our local cosmic neighbourhood, they noticed that many of them were drifting in similar directions. Galaxies in the local group and nearby structures were not only moving toward massive clusters like the Virgo cluster, they were also moving away from the underdense region. This pattern made sense from a gravitational perspective. Imagine standing between two large hills separated by a wide valley. If you release a ball near the valley's edge, it will tend to roll toward whichever hill exerts the stronger pull. In cosmic terms, galaxies behave in a similar way. They respond to the gravitational influence of nearby mass concentrations. Regions rich in galaxies and dark matter exert stronger gravitational pulls. Regions with little matter exert weaker pulls. If a galaxy sits near the boundary between those two environments, it will gradually drift toward the denser region. That's exactly what astronomers observed near the suspected void. Galaxies appeared to be migrating away from the empty region and toward the denser filaments and clusters surrounding it. This behaviour strongly suggested that the underdense region was real. Over time, astronomers began referring to it more confidently as the local void. Even then, however, the exact boundaries of the void remained uncertain. Because parts of it lay behind the dusty plane of the Milky Way, researchers needed better tools to probe that hidden region. New technologies gradually helped solve that problem. Infrared telescopes allowed astronomers to see through much of the interstellar dust that blocks visible light. Infrared wavelengths pass through dust more easily, revealing objects that would otherwise remain hidden. Radio telescopes also played an important role. Many galaxies contain large amounts of neutral hydrogen gas, which emits radiation at a specific radio wavelength known as the 21 centimeter line. This emission can travel through dust clouds that would completely block optical light. By scanning the sky at radio wavelengths, astronomers could detect galaxies even if their starlight was obscured. Using these techniques, scientists gradually began filling in the missing pieces of the map, and what they found confirmed that the local void was not an illusion caused by observational limitations. Even after accounting for galaxies hidden behind the Milky Way's dust, the region still contained far fewer galaxies than average. The void was real. The more astronomers studied it, the more intriguing it became. Most cosmic voids are discovered far away in large galaxy surveys that map regions hundreds of millions or billions of light-years from Earth. In those cases, the voids appear as distant cavities in the cosmic web. But the local void is different. It lies very close to our cosmic neighbourhood. In fact, the Milky Way appears to sit right along its boundary. That position offers astronomers a unique opportunity. Because we are located near the edge of the void, we can observe how it influences the motion of nearby galaxies. The local void is not just a distant feature on a map. It is part of the environment shaping the motion of our own galaxy. Observations suggest that the Milky Way and several neighbouring galaxies are moving away from the void at a modest speed. The motion is subtle, but measurable. It arises because galaxies on the opposite side of our neighbourhood exert stronger gravitational pulls than the nearly empty region behind us. This gravitational imbalance gently nudges galaxies away from the void over billions of years. The process is slow enough that no one would ever notice it on human timescales. But across cosmic time, the effect becomes significant. The local void gradually expands as matter flows outward from its interior, and that expansion has important consequences for the structure of the universe. As voids grow larger, the filaments and clusters surrounding them become more pronounced. Matter accumulates along the boundaries between voids, forming the long chains of galaxies that define the cosmic web. In other words, voids play a crucial role in shaping the large-scale architecture of the universe. Without them, the cosmic web would not exist in its familiar form. The discovery of the local void therefore offered astronomers a valuable laboratory for studying how underdense regions evolve. By examining the motions of nearby galaxies and mapping their positions in detail, researchers could observe the effects of a void from relatively close range. Yet one major question remained. Exactly how large was this empty region? Early estimates varied considerably. Some maps suggested the void might span roughly 30 million light-years across. Others hinted that it could be much larger, perhaps exceeding 100 million light-years. Part of the uncertainty arose from the difficulty of detecting extremely faint galaxies. Even the most advanced telescopes can miss small or dim galaxies lurking in the darkness. Each time astronomers discovered a new galaxy near the suspected boundary of the void, the map had to be updated. Gradually the picture improved. Large surveys using powerful telescopes began identifying additional galaxies near the edges of the void, helping define its boundaries more clearly. But even today, astronomers continue refining those measurements. The local void is not a simple sphere carved neatly out of space. Its edges are irregular, and its interior may contain a handful of faint galaxies scattered across enormous distances. Understanding its true size requires careful analysis of both galaxy positions and galaxy motions. At first glance, measuring something that is mostly empty might sound like an impossible task. If you wanted to measure the size of a mountain, you could look at its slopes and peak. If you wanted to measure the diameter of a planet, you could observe its surface or its shadow. Even a distant galaxy reveals its shape through the glow of billions of stars. But a cosmic void does not shine. It does not have a clearly defined surface. In many ways, it is simply a region where fewer galaxies exist than we would normally expect. So how do astronomers measure something defined mostly by the absence of objects? The answer, as it often is in science, comes from careful mapping. Astronomers begin by locating as many galaxies as possible across a given region of space. Each galaxy acts like a marker placed within the cosmic landscape. When enough markers are plotted, patterns begin to emerge. Dense regions fill with points representing galaxies, while sparse regions begin to reveal themselves as gaps. But mapping the universe is not quite as simple as drawing dots on a page. galaxies appear scattered across the sky in 2 dimensions when we observe them from Earth. To understand their true positions, astronomers must also determine how far away each galaxy lies. Only then can they build a 3-dimensional map of the cosmic environment. This is where the technique known as redshift measurement becomes essential. As we mentioned earlier, the universe is expanding. Galaxies that are farther away from us are generally moving away faster due to this expansion. When light travels from those galaxies toward Earth, the stretching of space causes the light's wavelength to lengthen slightly. This shift toward longer wavelengths is called redshift. By measuring how much the light from a galaxy has shifted, astronomers can estimate its distance. The greater the redshift, the farther away the galaxy is likely to be. Once that distance is calculated, the galaxy can be placed into a 3-dimensional cosmic map. Now imagine repeating that process for thousands of galaxies, then tens of thousands, then millions. Over time, astronomers have built enormous catalogues containing the positions and distances of galaxies across large portions of the sky. Some of the most famous surveys include projects like the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey, which have mapped the locations of millions of galaxies. When scientists visualize the results of these surveys, the universe reveals its large-scale structure. Filaments of galaxies stretch across space like delicate threads. Dense clusters appear as bright knots where many galaxies gather together. And between those structures lie vast cavities where relatively few galaxies reside. Those cavities are the voids. The local void was identified using exactly this kind of mapping. Astronomers examined the distribution of nearby galaxies and noticed a region where the density dropped dramatically. But identifying a void is only the first step. Measuring its size is a little more complicated. Unlike planets or stars, voids do not have sharp boundaries. There is no precise line where the void suddenly begins or ends. Instead, the density of galaxies gradually increases as you move from the center of the void toward the surrounding filaments. Astronomers therefore define a void's boundary using statistical thresholds. In simple terms, they determine how dense the region is compared with the average density of galaxies in the universe. If the density falls below a certain level, the region may be classified as part of a void. Researchers then analyze the shape of that underdense region and estimate its overall dimensions. In practice, this process often involves computer algorithms that search galaxy maps for large connected regions of low density. These algorithms can identify void candidates and estimate their sizes based on the positions of nearby galaxies. Some voids turn out to be relatively simple shapes, roughly spherical or slightly elongated. Others are far more irregular, resembling distorted bubbles that merge into neighbouring voids. The local void belongs to the second category. Its boundaries are uneven and somewhat difficult to define precisely. Part of it stretches behind the Milky Way's plane, where dust obscures distant galaxies. Other portions extend outward into regions that have only recently been mapped in detail. Because of this complexity, astronomers often rely on additional clues beyond galaxy positions. One of the most useful clues comes from galaxy motion. Galaxies do not remain stationary in space. They drift slowly under the influence of gravitational forces from nearby structures. By measuring the velocities of galaxies relative to one another, astronomers can learn how mass is distributed throughout the universe. If galaxies are moving away from a particular region, it may indicate that the region contains very little matter. This technique has been particularly useful in studying the local void. Observations show that many galaxies in our local cosmic neighbourhood are drifting away from the direction of the void. That motion suggests that the void contains relatively little mass compared with surrounding regions. In effect, the void behaves like a cosmic valley from which galaxies gradually flow outward. Another helpful technique involves measuring the distances to galaxies using methods other than redshift. Redshift provides a good estimate of distance when galaxies are very far away, but nearby galaxies can have additional motions caused by local gravitational interactions. These motions can complicate redshift-based distance measurements. To improve accuracy, astronomers sometimes use standard candles. A standard candle is an astronomical object whose intrinsic brightness is well understood. By comparing how bright the object appears from Earth with how bright it truly is, scientists can estimate its distance. One famous example of a standard candle is the Cepheid variable star. These stars brighten and dim in a regular pattern, and the timing of their brightness variations is directly related to their true luminosity. Another widely used standard candle is the Type 1a supernova, a particular kind of stellar explosion that produces a very predictable brightness. By identifying these objects within galaxies, astronomers can measure distances more precisely and refine their maps of the nearby universe. For regions like the local void, these improved distance measurements help confirm that certain areas truly contain very few galaxies. But there is yet another method that offers insight into the distribution of matter across large scales. Astronomers can observe the cosmic microwave background, the faint afterglow of the Big Bang that fills the entire universe. Tiny variations in this radiation reveal the initial density fluctuations that eventually grew into galaxies, clusters, and voids. When scientists analyze these fluctuations and compare them with modern galaxy surveys, they find that the locations of voids correspond remarkably well with regions that began slightly underdense in the early universe. This connection provides strong evidence that voids formed naturally as gravity amplified those early differences over billions of years. Simulations of cosmic evolution also play an important role. Using powerful supercomputers, researchers simulate the expansion of the universe and the gravitational interactions of dark matter over time. These simulations begin with conditions similar to those observed in the early universe and then evolve forward across billions of years. The results consistently produce a cosmic web of filaments and voids very similar to what astronomers observe. By comparing real galaxy maps with these simulations, scientists can estimate the size and structure of voids like the local void. Gradually, a clearer picture begins to emerge. Current estimates suggest that the local void extends roughly 150 million light-years across, though different studies sometimes propose slightly different values depending on how the boundaries are defined. What remains certain is that the void is enormous. Even the smallest cosmic voids dwarf the size of individual galaxies. The local void is large enough that light would require many tens of millions of years to cross from one side to the other. And yet, within that vast region, the number of galaxies remains surprisingly small. Astronomers continue searching for faint galaxies hidden within the void. Some discoveries have been made, particularly using radio telescopes capable of detecting hydrogen gas in extremely dim galaxies. These galaxies often appear small and isolated, drifting quietly through space with few nearby companions. Their existence reminds us that voids are rarely completely empty. Instead, they contain scattered remnants of matter that never gathered into the dense structures seen elsewhere in the cosmic web. Understanding these isolated galaxies can reveal important details about how galaxies form under different environmental conditions. Just how large is this enormous region of emptiness? Just how empty is the local void? Even with modern surveys and advanced telescopes, scientists are still refining their measurements. New observations continue to reveal faint galaxies near the edges of the void, gradually sharpening our picture of its true structure. Each discovery helps answer a question that once seemed almost impossible. How do you measure nothing? Trying to measure the size of something that is mostly empty requires a certain amount of patience. Astronomers cannot simply point a telescope toward the sky and see the outline of the local void the way we might see the edge of a cloud or the disk of a distant planet. Instead, they must rely on the distribution of galaxies surrounding the void to trace its boundaries. Imagine standing on a hill and looking down at a wide valley at night. If the valley were filled with houses, the lights would outline its shape clearly. But if the valley were mostly empty, you might only see scattered lights around the edges where towns begin again. By studying where those lights appear and where they disappear, you could slowly estimate the size of the valley. Astronomers use a similar approach when studying cosmic voids. The local void reveals itself through the galaxies that lie around it. By mapping those galaxies in 3 dimensions and observing where their density drops dramatically, scientists can begin to estimate how large the void must be. Over the past several decades, improved surveys of nearby galaxies have allowed astronomers to refine this map. Each new observation adds another marker in the cosmic landscape, helping researchers determine where the void likely begins and where it gradually blends into the surrounding filaments of galaxies. The numbers that emerge from these studies are striking. Many astronomers estimate that the local void spans roughly 150 million light-years across, although the exact value depends on how its boundaries are defined. Some estimates suggest portions of the void may extend even farther when connected to neighbouring underdense regions. To appreciate how large that really is, it helps to compare the void with more familiar cosmic structures. Our home galaxy, the Milky Way, is about 100,000 light-years wide. Even that distance is difficult to picture. Light travelling at nearly 300,000 kilometers per second still takes 100,000 years to cross the galaxy from one side to the other. Now, imagine placing the Milky Way inside the local void. You could fit more than 1,000 galaxies the size of the Milky Way across the diameter of the void, and the void would still have room to spare. Another useful comparison involves the local group, the small collection of galaxies that includes the Milky Way and the Andromeda Galaxy. The local group spans roughly 10 million light-years from one side to the other. That entire structure could fit inside the local void many times over. Even larger galaxy clusters appear small when compared with the scale of this empty region. The Virgo cluster, which contains thousands of galaxies and dominates the gravitational landscape of our nearby universe, spans about 10 million light-years as well. Again, that entire cluster could fit comfortably inside the local void. This comparison helps illustrate just how enormous these cosmic cavities truly are. Yet the void is not a perfectly round bubble floating in space. Its shape is more irregular and complex. Instead of smooth, spherical boundaries, the local void appears to have uneven edges defined by the surrounding filaments and galaxy groups. Some portions of the void extend farther than others. In certain directions, the boundary lies relatively close to our galaxy, perhaps only 20 or 30 million light-years away. In other directions, the underdense region stretches much farther. One of the reasons the void's shape remains somewhat uncertain is the presence of the Milky Way itself. Our galaxy contains dense clouds of gas and dust concentrated along its central plane. When astronomers try to observe distant galaxies in that direction, the dust absorbs and scatters much of the incoming light. The result is a band across the sky where distant galaxies are difficult to detect. This region, sometimes called the zone of avoidance, complicates attempts to map the local void completely. Portions of the void may lie hidden behind the Milky Way's dusty disk, making them difficult to observe using ordinary optical telescopes. To overcome this challenge, astronomers use infrared and radio observations that can penetrate much of the dust. These techniques have gradually revealed galaxies previously hidden behind the plane of the Milky Way. Each newly discovered galaxy helps refine the outline of the void. Even with these advances, however, the boundaries remain somewhat fuzzy. Voids rarely have clear edges. Instead, the density of galaxies gradually increases as you move outward toward the surrounding filaments of the cosmic web. Because of this gradual transition, different studies sometimes define the void's boundary in slightly different ways. Some researchers focus on regions where galaxy density drops below a certain fraction of the cosmic average. Others examine the motion of galaxies to determine where the gravitational influence of surrounding structures becomes dominant. Despite these differences, most measurements agree that the local void is extremely large. It is one of the most significant underdense regions in our immediate cosmic neighbourhood. Another way astronomers estimate the size of the void involves studying the motions of nearby galaxies. Galaxies do not remain stationary in space. They move under the influence of gravitational forces exerted by surrounding matter. By measuring the velocities of galaxies relative to the Milky Way, scientists can infer how mass is distributed across nearby regions of the universe. When astronomers examine the motion of galaxies near the local void, they observe a consistent pattern. Many galaxies appear to be drifting away from the direction of the void. This motion is subtle but measurable. It suggests that the void contains relatively little mass compared with surrounding regions. As a result, galaxies feel a stronger gravitational pull from denser structures located elsewhere. The effect can be thought of as a kind of gravitational imbalance. Imagine floating between two groups of people, pulling gently on opposite ends of a rope. If one group is much larger than the other, you will slowly drift toward the stronger side. In the cosmic version of this scenario, the larger group represents dense clusters and filaments of galaxies. The smaller group represents the relatively empty region of the void. Over billions of years, galaxies gradually move away from the underdense region and toward areas where more mass is concentrated. This motion helps astronomers determine how far the influence of the void extends. When scientists map these motions carefully, they find that galaxies within tens of millions of light-years appear to be moving outward from the void's interior. That observation supports the idea that the local void occupies a large volume of space adjacent to our cosmic neighbourhood. Another important clue comes from cosmological simulations. Researchers use powerful supercomputers to simulate the evolution of the universe, from shortly after the Big Bang to the present day. These simulations track billions of particles representing dark matter and ordinary matter as they interact through gravity. As the simulated universe evolves, matter naturally organizes itself into filaments and clusters, leaving behind enormous voids between them. When scientists compare these simulations with real galaxy surveys, they find that the predicted sizes of voids match observations quite well. Voids ranging from tens to hundreds of millions of light-years are a natural outcome of cosmic evolution. The local void fits comfortably within that expected range. But perhaps the most remarkable aspect of the local void is not just its size, but its location. Many large voids exist far from our galaxy, scattered throughout the cosmic web. The Bhuta's void, for example, lies hundreds of millions of light-years away. The local void, by contrast, sits right next to us. Our galaxy occupies a position along the boundary between the void and a more densely populated region of the universe. That placement has subtle consequences for the motion of the Milky Way itself. Astronomers estimate that our galaxy is moving away from the void at a speed of roughly 260 kilometers per second. This motion contributes to the overall velocity of the local group relative to the cosmic microwave background. The local void, in other words, is not just an empty region of space. It is an active part of the gravitational landscape shaping our cosmic environment, and the void itself continues to evolve. As the universe expands, underdense regions like the local void tend to grow larger. Matter flows outward from the void's interior and accumulates along its boundaries, strengthening the surrounding filaments. Over billions of years, the void slowly expands while the cosmic web becomes more pronounced. This process is still ongoing today. The local void will likely continue growing as the universe ages, becoming even emptier and larger over time. Once astronomers began mapping galaxies across truly enormous distances, the picture that emerged was both surprising and strangely elegant. The universe, when viewed on its larger scales, does not resemble a random scattering of galaxies floating in empty space. Instead, it forms a pattern that looks remarkably similar to a vast network of bubbles. This comparison may sound unusual at first, but it turns out to be a helpful way of visualizing the large-scale structure of the cosmos. Imagine dipping a wire loop into a container of soap solution and blowing gently. A cluster of bubbles forms. Each bubble presses against its neighbours, creating a delicate arrangement of curved walls and empty interiors. The soap films form thin surfaces separating pockets of air, while the air inside each bubble remains mostly empty. Now imagine expanding that pattern across hundreds of millions of light-years. In the cosmic version of this structure, The thin soap walls are replaced by filaments and sheets of galaxies. These filaments stretch across enormous distances, linking galaxy clusters together into a vast interconnected web. The interiors of the bubbles correspond to cosmic voids. Regions like the local void occupy those enormous interior spaces. When astronomers examine galaxy maps covering large volumes of the universe, the resemblance to foam becomes striking. Filaments of galaxies outline enormous cavities, giving the universe a structure that can sometimes be described as sponge-like or bubble-like. In fact, many cosmologists use the term cosmic foam to describe this pattern. The idea is simple. Galaxies do not fill space uniformly. Instead, they trace the surfaces and edges of enormous bubbles that formed as the universe evolved. The local void is just one of those bubbles, but to understand why the universe ended up with this bubble-like arrangement, we need to return briefly to the early stages of cosmic history. Shortly after the Big Bang, the universe was extremely hot and dense. Matter existed mostly as a glowing plasma of particles and radiation. During this period, the distribution of matter was nearly uniform, but not perfectly so. Tiny fluctuations in density existed from the very beginning. Some regions contained slightly more matter than average. Other regions contained slightly less. At first, those differences were incredibly small, only a few parts in 100,000. But gravity has a remarkable ability to amplify even the tiniest variations over time. The slightly denser regions began pulling in additional matter. As they grew more massive, their gravitational pull strengthened, drawing in even more material from surrounding space. Meanwhile, regions that began slightly underdense lost matter as it flowed toward the growing structures nearby. Over millions and then billions of years, this process gradually sculpted the universe into its present form. Dense regions became clusters of galaxies and long filaments connecting them. Underdense regions became cosmic voids. The result was the cosmic web. In this web, galaxies gather along filaments that can stretch for hundreds of millions of light years. These filaments intersect at nodes where galaxy clusters form. Between them lie enormous voids that contain relatively little matter. From a distance, the pattern resembles bubbles packed together in 3 dimensions. Each bubble represents a region where matter has drained away over time. The local void fits naturally into this picture. It is one bubble among many within the cosmic foam, though its proximity to our galaxy makes it particularly interesting. One of the most fascinating aspects of these bubbles is that they are not static. They evolve as the universe expands. Voids tend to grow larger over time. This might seem surprising at first, but the explanation is quite straightforward. Because voids contain relatively little matter, they exert weaker gravitational pull compared with surrounding regions. As the universe expands, matter tends to flow outward from the void and accumulate along its edges. This process gradually enlarges the void while strengthening the surrounding filaments. In other words, the cosmic bubbles slowly expand as time passes. Computer simulations of the universe show this behavior very clearly. When researchers simulate billions of particles interacting through gravity over cosmic time, the particles naturally organize themselves into a network of filaments and voids. The voids expand while the filaments become more pronounced. The resulting structure looks remarkably similar to real galaxy surveys. This agreement between observation and simulation provides strong support for our current understanding of cosmic structure formation. But the bubble analogy does not stop there. Just as soap bubbles can merge with one another, cosmic voids can also grow by combining with neighbouring voids. As matter flows outward from underdense regions, adjacent voids may gradually expand until they meet and merge. Over time, this process can create extremely large voids composed of several smaller cavities that have joined together. The local void may be part of such a larger structure. Some studies suggest that it connects with other underdense regions nearby, forming an extended network of emptiness stretching across hundreds of millions of light years. If that interpretation is correct, the local void might represent only a portion of a much larger bubble in the cosmic foam. Yet despite their immense size, voids are not completely empty. Astronomers have discovered small numbers of galaxies drifting through these regions. These galaxies are typically isolated and widely separated from one another. In the crowded regions of the universe, galaxies often interact gravitationally. They may collide, merge, or distort each other through close encounters. Inside voids, those interactions are far less common. A galaxy living inside a void may go billions of years without experiencing a close encounter with another galaxy. This isolation can have interesting consequences for how galaxies evolve. Many void galaxies appear relatively small and rich in gas. Without frequent collisions to trigger bursts of star formation, their development may proceed more slowly and quietly. Some astronomers compare these galaxies to peaceful rural communities, in contrast with the busy metropolitan regions represented by dense galaxy clusters. Studying them helps researchers understand how environment influences galaxy evolution. Another fascinating aspect of the bubble-like universe is how galaxies move along the boundaries of voids. Gravity draws matter toward dense regions, but the absence of mass inside voids also plays a role. Because voids contain less matter, galaxies near their edges experience stronger gravitational pulls from surrounding filaments and clusters. Over time, galaxies drift away from the void interiors and accumulate along the walls between bubbles. This process helps sharpen the boundaries of the cosmic web. It is similar to the way soap films form where bubbles press against one another. The galaxies trace the edges of the bubbles, outlining the large-scale structure of the universe. The local void sits beside one of these boundaries. On one side of our galaxy lies the emptiness of the void. On the other side lie richer regions of the cosmic web containing galaxy groups, clusters, and long filaments of matter. This position means the Milky Way occupies an interesting place within the bubble structure. We are not deep inside the void, nor are we located within the densest clusters of galaxies. Instead, we reside along one of the edges of a cosmic bubble. This location offers astronomers a unique opportunity to study how voids influence the motion of galaxies nearby. As we discussed earlier, observations show that our galaxy and its neighbours appear to be drifting away from the local void. That motion is small, but measurable. It occurs because galaxies are pulled toward denser structures, while the void exerts relatively little gravitational influence. The local void therefore behaves somewhat like a gentle gravitational valley, encouraging matter to flow outward from its interior. This flow contributes to the large-scale movements of galaxies across the cosmic web. The idea that the universe resembles a collection of bubbles might seem abstract at first, but it turns out to be one of the most powerful ways to visualize cosmic structure. Instead of imagining galaxies scattered randomly through space, we can think of them as tracing the boundaries of enormous cavities formed by gravity over billions of years. These cavities dominate the volume of the universe. The local void is one of them. And although it may appear empty at first glance, its presence helps shape the motion of galaxies across millions of light years. But within that enormous bubble of space, a few galaxies still exist. They drift quietly through the darkness, separated from their nearest neighbours by immense distances. Those lonely galaxies offer an unusual window into the conditions inside cosmic voids, and their existence raises a natural question: what exactly lives inside a void? Far from the crowded intersections of the cosmic web, there are places where the universe becomes noticeably quieter. In these regions, galaxies are not packed together in clusters or stretched along busy filaments. Instead, they appear only occasionally, separated by enormous distances of darkness. These are the interiors of cosmic voids, including the vast region we've been discussing, the local void. It might be tempting to imagine that such places contain absolutely nothing. After all, the word void suggests a perfect emptiness, a region stripped entirely of matter. But the universe rarely produces absolute extremes. Even in the emptiest regions known to astronomers, there are still traces of structure, small remnants of matter that never fully migrated toward the dense filaments and clusters elsewhere in the cosmic web. So the more accurate description is that voids are not completely empty, they are simply very, very quiet. Inside these enormous regions of space, astronomers occasionally find galaxies. Not many of them, certainly not the dense gatherings seen in clusters, but enough to remind us that gravity rarely leaves a region entirely untouched. These galaxies are sometimes called void galaxies, and they represent some of the most isolated large structures in the universe. To understand just how isolated they are, it helps to compare them with galaxies living in crowded regions of space. In dense galaxy clusters, individual galaxies may be separated by only a few 100,000 light-years. That distance is large on human scales, but cosmically speaking it is relatively close. Galaxies and clusters frequently interact with one another through gravity. They pass near each other, tugging on each other's stars and gas. Sometimes they collide and merge, forming larger galaxies. These interactions shape the evolution of galaxies dramatically. In a crowded cluster, galaxies can lose gas through gravitational stripping. Their shapes may become distorted. Star formation can be triggered by collisions or tidal forces. The environment is active, dynamic, and occasionally chaotic. Inside a void, the situation is very different. A void galaxy may be tens of millions of light-years away from its nearest significant neighbour. That means gravitational interactions occur far less often. A galaxy drifting through a void might go billions of years without experiencing a close encounter with another galaxy. This isolation changes the way galaxies evolve. One of the first things astronomers noticed about void galaxies is that many of them appear relatively small. Large spiral galaxies like the Milky Way are less common in voids, though they do exist. Instead, researchers frequently observe dwarf galaxies and modest spiral galaxies with fewer stars. These galaxies often retain large amounts of gas. In more crowded environments, gas can be stripped away through interactions with neighbouring galaxies or with the hot gas that fills galaxy clusters. But in the quiet environment of a void, those processes are far less common. As a result, void galaxies sometimes contain significant reservoirs of hydrogen gas that can fuel star formation for long periods of time. Astronomers have also observed that star formation in void galaxies tends to proceed differently from that in cluster galaxies. Without frequent disturbances, star formation may occur more gradually and steadily. The galaxy slowly converts gas into stars over billions of years, rather than experiencing sudden bursts triggered by interactions. This calmer evolution can produce galaxies with relatively simple structures. Another interesting feature of void galaxies is their shape. Because they experience fewer gravitational interactions, many void galaxies retain fairly regular forms. Spiral arms may remain well defined. Disks remain relatively undisturbed. In contrast, galaxies in crowded regions often show signs of distortion caused by gravitational encounters. Some void galaxies appear almost pristine compared with their cluster-dwelling cousins. Studying these galaxies allows astronomers to observe how galaxies evolve when left largely alone. In that sense, void galaxies act as natural laboratories. By comparing them with galaxies in dense environments, researchers can learn how much of galaxy evolution depends on external influences. Yet even inside the vast emptiness of a cosmic void, galaxies rarely exist in complete solitude. Sometimes a void galaxy will have a few small companions, dwarf galaxies that formed nearby and remained gravitationally bound. These small groups are still extremely isolated compared with typical galaxy clusters, but they demonstrate that void interiors are not perfectly uniform. Instead, they contain small pockets of matter that never fully migrated toward the filaments of the cosmic web. Another important component of void interiors is dark matter. Although voids contain less dark matter than surrounding regions, they are not completely devoid of it. Dark matter still forms a faint underlying structure throughout the universe. Even inside voids, thin distributions of dark matter remain present. These dark matter structures help explain why galaxies can form inside voids at all. If a region contains even a modest concentration of dark matter, gravity can still gather gas and eventually form stars. Over long timescales, This process can produce small galaxies drifting through otherwise empty regions of space. Computer simulations of cosmic structure formation show this process clearly. When researchers simulate the evolution of dark matter across billions of years, the resulting structure resembles the cosmic web we observe. Dense filaments form where dark matter collects, while large voids develop in regions where matter has drained away. But even inside these simulated voids, a few isolated pockets of dark matter remain. These pockets can give rise to small galaxies. That is why astronomers occasionally discover galaxies inside regions that otherwise appear nearly empty. The local void itself appears to contain a small number of such galaxies. Detecting them is not always easy. Many of these galaxies are faint and small, making them difficult to observe from Earth. Some are hidden behind the dusty plain of the Milky Way, further complicating the search. However, with the help of modern telescopes and radio surveys that detect hydrogen gas, astronomers have gradually identified several galaxies residing inside the local void. Each discovery helps researchers better understand the conditions inside this enormous region. Another intriguing aspect of void galaxies is how slowly they move relative to one another. In dense clusters, gravitational interactions can accelerate galaxies to speeds of thousands of kilometers per second. Galaxies may pass each other at tremendous velocities as they orbit within the cluster's gravitational field. Inside voids, galaxy motions are typically more subdued. Because the gravitational environment is weaker, galaxies drift more gently through space. Their velocities relative to neighbouring galaxies tend to be lower, reflecting the quieter environment of the void interior. This difference in motion provides another clue for astronomers studying voids. By measuring galaxy velocities, scientists can estimate the gravitational forces acting within a region. In voids, those forces are noticeably weaker. Yet even though void galaxies live in relative isolation, they're not entirely disconnected from the rest of the universe. Over very long timescales, gravity continues to shape their environment. Galaxies near the edges of a void gradually drift toward the surrounding filaments, where matter is more abundant. As this happens, the void slowly expands, and the galaxies that once lived near its centre may eventually move closer to the boundaries. This process is slow enough that it unfolds over billions of years. In cosmic terms, however, it is an important part of how the large-scale structure of the universe evolves. Voids grow larger while filaments become more pronounced. The local void participates in this same process. Although it appears calm and quiet today, the region is slowly changing as galaxies and dark matter drift under the influence of gravity. The galaxies inside the void may remain isolated for immense periods of time, but eventually some of them may approach the boundaries, where the cosmic web becomes denser. When that happens, their environment may change dramatically. Interactions with other galaxies could begin for the first time in billions of years. Gas clouds might be disturbed, triggering new waves of star formation. For now, though, the galaxies inside the local void remain among the most isolated objects known in the universe. They drift quietly through enormous volumes of space, separated from their nearest neighbours by distances that would dwarf even the largest galaxy clusters. Their existence reminds us that even in the emptiest regions of the cosmos, structure still persists, and their quiet presence inside the local void provides astronomers with valuable clues about how galaxies form and evolve when left almost entirely alone. Gravity is usually associated with things that are massive and visible. Planets pull on moons, stars hold their planets in orbit. Entire galaxies remain bound together because of the gravity produced by billions of stars and enormous halos of dark matter. In everyday thinking, gravity feels like a force created by the presence of matter. That intuition is mostly correct. But when astronomers examine the largest structures in the universe, they discover something slightly counterintuitive. Regions that contain very little matter can influence the motion of galaxies just as much as regions that contain a great deal of it. This effect becomes especially noticeable near cosmic voids. To understand why, it helps to think about gravity not as a force pushing or pulling in isolation, but as part of a larger gravitational landscape. Imagine the universe as a vast terrain with hills and valleys created by the distribution of matter. Dense regions, such as galaxy clusters, form the deepest gravitational valleys. Less dense regions form shallower slopes. Voids, by contrast, represent areas where the gravitational landscape is unusually flat. If a galaxy sits near a massive cluster, gravity pulls it strongly toward that region. But if the galaxy sits near a void, there is very little mass inside that region to exert any gravitational pull at all. This difference matters more than it might first appear. Picture a ball resting between two hills. One hill is tall and steep, while the other is low and gentle. The ball will naturally roll toward the steeper side because gravity there is stronger. Galaxies behave in a similar way. When a galaxy lies near the boundary between a dense region and an underdense one, the gravitational pull from the dense region dominates. Over time, the galaxy drifts toward that side, gradually moving away from the emptier region. In this way, the presence of a void can influence the motion of galaxies even though the void itself contains very little matter. Astronomers sometimes describe this phenomenon as void repulsion, though the term can be slightly misleading. Nothing is actually pushing galaxies away from the void. Instead, galaxies simply feel a stronger gravitational attraction from the surrounding regions where matter is concentrated. Because the void lacks mass, it contributes very little to the gravitational balance. The result is a net motion away from the empty region. This subtle effect becomes easier to observe when astronomers examine the velocities of galaxies in our cosmic neighbourhood. Galaxies do not simply follow the expansion of the universe. They also possess what astronomers call peculiar velocities, motions caused by gravitational interactions with nearby structures. For example, our local group of galaxies is moving toward the Virgo cluster because that cluster contains enormous amounts of mass. The gravitational attraction of Virgo gently pulls nearby galaxies in its direction. But that is not the only motion affecting our galaxy. Careful measurements show that the Milky Way and several nearby galaxies are also moving away from the direction of the local void. The speed involved is modest on cosmic scales, roughly a few hundred kilometers per second. That may sound fast, but compared with the expansion of the universe or the motions inside galaxy clusters, it is relatively gentle. Even so, the effect becomes significant when considered over billions of years. The local void appears to contribute to the motion of our galaxy by creating a gravitational imbalance between the emptier region behind us and the denser structures ahead. In other words, the Milky Way is not only being pulled toward dense clusters like Virgo, it is also drifting away from the vast emptiness beside it. Astronomers sometimes refer to this combined motion as part of a cosmic flow, the large-scale movement of galaxies through the universe. Mapping these flows helps researchers understand how matter is distributed across enormous distances. By analysing the velocities of thousands of galaxies, scientists can identify regions where matter is concentrated and regions where it is scarce. Voids stand out clearly in such maps because galaxies tend to move away from them. The local void is one of the most prominent examples of this effect in our nearby cosmic environment. But the gravitational influence of voids goes beyond simple galaxy motions. Voids also affect how matter accumulates along the boundaries of the cosmic web. As galaxies and dark matter drift outward from the interior of a void, they gradually gather along the edges where neighbouring voids meet. Over time, this process strengthens the filaments and walls of galaxies surrounding the void. In essence, voids help sculpt the large-scale structure of the universe. The cosmic web becomes sharper and more pronounced because matter continues to migrate away from underdense regions and toward denser ones. Computer simulations of cosmic evolution illustrate this process clearly. When researchers simulate the behavior of dark matter particles across billions of years, the particles tend to move outward from void interiors and accumulate along filamentary structures. The voids expand while the filaments grow thicker. These simulations closely match the galaxy distributions observed in real surveys. One of the most interesting aspects of void evolution is that voids tend to grow faster than the universe itself expands. This may sound surprising, but it follows naturally from their low density. Because voids contain relatively little matter, there is less gravitational resistance to the expansion of space inside them. As the universe expands, the matter surrounding the void continues drifting outward, effectively enlarging the empty region. The result is that voids gradually occupy an increasing fraction of the universe's total volume. Over extremely long timescales, the cosmic web may become even more dominated by vast empty cavities separated by thin filaments of matter. The local void participates in this process. Although it appears stable on human timescales, it is slowly expanding as galaxies and dark matter migrate away from its interior. The motion is incredibly slow from our perspective. At speeds of a few hundred kilometers per second, it would still take millions of years for a galaxy to move a noticeable distance relative to its neighbours. Yet across billions of years, these motions reshape the cosmic landscape. Another interesting effect involves how voids interact with neighbouring voids. Just as soap bubbles can merge together when their walls break down, cosmic voids can gradually combine as the filaments separating them thin out. When two voids merge, they form a larger cavity surrounded by newly strengthened boundaries. This process contributes to the growth of some of the largest voids in the universe. The local void itself may connect with nearby underdense regions in ways that astronomers are still studying. Because portions of the void lie behind the plane of the Milky Way, the full extent of its structure remains somewhat uncertain. As new observations reveal previously hidden galaxies, researchers continue refining the map of our local cosmic environment. Despite these uncertainties, the overall picture remains clear. The local void is not simply an empty patch of space that happens to sit beside our galaxy. It is an active part of the gravitational landscape shaping the motion of galaxies across millions of light years. Its presence contributes to the cosmic flow that carries our galaxy through the universe, and it plays a role in guiding matter along the filaments of the cosmic web. In this sense, emptiness itself becomes an important participant in cosmic evolution. It may not shine like a galaxy cluster or blaze like a supernova, but the absence of matter can influence the movement of galaxies across vast distances. This realization has changed how astronomers think about the universe. For many years, researchers focused primarily on the visible structures of the cosmos, galaxies, clusters, and filaments. But the discovery of voids revealed that the empty spaces between those structures are just as important. The cosmic web is shaped as much by the absence of matter as by its presence, and in our own cosmic neighbourhood, the local void offers a nearby example of this principle. When astronomers measure the motion of galaxies, they often discover that those motions are more complicated than they first expected. The universe is expanding, which means that on very large scales galaxies are gradually moving away from one another. But superimposed on that expansion are smaller movements caused by gravity. Galaxies are constantly responding to the uneven distribution of matter around them. In regions where matter gathers densely, gravity pulls nearby galaxies inward. In regions where matter is scarce, galaxies tend to drift away because there is little gravitational pull holding them there. These local motions are called peculiar velocities, and they can reveal surprising details about the large-scale structure of the universe. One of the most intriguing examples involves the motion of our own galaxy. The Milky Way is not simply drifting along with the expansion of the universe. Instead, it is moving through space with a measurable velocity relative to the cosmic microwave background, the faint radiation left over from the Big Bang that fills the universe in all directions. By studying tiny variations in this radiation, astronomers have determined that the Milky Way and its neighbouring galaxies are moving at roughly 600 kilometers per second relative to this cosmic reference frame. That motion has puzzled scientists for decades. What exactly is pulling or pushing our galaxy through space at such a speed? For a long time, the main explanation focused on large concentrations of mass located in the direction of the Virgo cluster and beyond. Virgo is the nearest major galaxy cluster to the Milky Way, containing thousands of galaxies and enormous quantities of dark matter. It exerts a powerful gravitational pull on surrounding structures, including our local group of galaxies. Beyond Virgo lies an even larger region of gravitational influence, sometimes referred to as the Great Attractor, a massive concentration of galaxies hidden partially behind the dense plane of the Milky Way. This region appears to contribute significantly to the motion of galaxies across hundreds of millions of light years. These massive structures clearly pull galaxies toward them. But when astronomers carefully examined the velocity of the Milky Way and nearby galaxies, they noticed something interesting. The direction of our motion could not be explained entirely by gravitational attraction from dense clusters alone. Part of the motion seemed to originate from the opposite direction. In other words, while the Virgo cluster and other dense regions were pulling us in one direction, something else appeared to be encouraging motion away from another part of the sky. That region, as researchers gradually realized, corresponded closely with the location of the local void. This observation raised a fascinating possibility. Perhaps the Milky Way is not only being pulled toward dense clusters of galaxies, but also drifting away from the enormous underdense region next door. In everyday language, it might sound as though the local void is pushing our galaxy away. In reality, the physics is a bit subtler than that. Voids do not generate forces that push objects outward. Instead, their influence arises from the relative absence of gravitational pull. Because there is very little matter inside the void, galaxies near its boundary feel a stronger attraction from the denser structures located elsewhere. The result is a gradual drift away from the void. Astronomers sometimes describe this process as void expansion. As matter flows outward from underdense regions, the void grows larger, while the surrounding filaments and clusters become more pronounced. Our galaxy appears to be participating in this process. Measurements of galaxy velocity suggest that the local group, the small collection of galaxies that includes the Milky Way and Andromeda, is moving away from the local void at a speed of roughly 260 kilometers per second. That speed is only one component of our galaxy's overall motion through space, but it is large enough to be significant. To visualize what is happening, imagine standing on the edge of a wide valley surrounded by hills. If the valley contains very little mass while the hills contain much more, gravity will tend to pull objects toward the hills. In the cosmic version of this situation, the hills correspond to regions filled with galaxies and dark matter. The valley corresponds to the local void. Over billions of years, galaxies near the boundary gradually drift toward the denser terrain. Because the Milky Way sits close to that boundary, it experiences this effect as well. Astronomers have confirmed this behavior by studying the motions of nearby galaxies in 3 dimensions, by measuring redshifts and distances using various techniques. Scientists can determine not only how far galaxies are from us, but also how they are moving relative to one another. When these velocities are plotted on large maps of the nearby universe, a pattern emerges. Galaxies near the local void appear to be moving outward from its interior, as though they are sliding down gentle gravitational slopes toward denser regions of the cosmic web. This pattern provides strong evidence that the local void plays an active role in shaping galaxy motion across our region of space. It also highlights an interesting feature of the cosmic web. Voids are not merely empty spaces between filaments. They are dynamic components of the gravitational landscape. Their presence influences the flow of matter across enormous distances. Computer simulations of cosmic evolution show this behavior very clearly. When researchers simulate the expansion of the universe and the gravitational interactions of dark matter over billions of years, they observe that matter gradually drains away from underdense regions. Galaxies migrate toward filaments and clusters, while voids expand. The local void appears to follow the same pattern. Over time, the region grows larger as matter flows outward along its boundaries. This expansion contributes to the peculiar velocities of nearby galaxies, including our own. Another interesting consequence of this motion involves the cosmic microwave background. Because the Milky Way is moving through space, the cosmic microwave background appears slightly warmer in the direction we are moving and slightly cooler in the opposite direction. This effect is known as the dipole anisotropy of the cosmic microwave background. By measuring this temperature difference with extraordinary precision, astronomers can determine the speed and direction of our galaxy's motion. When researchers analyse this motion in detail, they find that it aligns closely with the combined influence of several large structures. Dense clusters of galaxies pull us in one direction. The local void contributes by creating a gravitational imbalance that encourages motion away from its interior. Together, these effects produce the overall velocity we observe. In this sense, the Milky Way's journey through space reflects the complex interplay of gravity across the cosmic web. We're not drifting randomly through the universe. Our galaxy is responding to the distribution of matter across millions of light years. Clusters pull us inward, voids allow us to drift outward, and the result is a slow but measurable motion that carries the Milky Way through the surrounding structure of the universe. Of course, this motion unfolds extremely slowly on human timescales. Even travelling at several hundred kilometres per second, our galaxy moves only a small fraction of a light year in 1,000 years. Compared with the immense distances separating galaxies, that motion is barely noticeable. But across billions of years, it reshapes the cosmic environment. Galaxies that once sat near the centres of voids may eventually migrate toward filaments and clusters. New structures form as matter accumulates along the boundaries between expanding voids. The cosmic web slowly evolves. Our galaxy's position near the edge of the local void provides a rare opportunity to observe these processes from relatively close range. Instead of studying a void located hundreds of millions of light years away, astronomers can analyse the influence of one that lies right beside our cosmic neighbourhood. This proximity has allowed researchers to map galaxy motions with remarkable detail. Each new measurement helps refine our understanding of how the local void contributes to the gravitational dynamics of our region of space. Across the universe, galaxies rarely sit still. Even though the distances between them are enormous and the timescales involved stretch across billions of years, galaxies are constantly drifting under the influence of gravity. When astronomers map those motions carefully, a remarkable pattern begins to appear. Galaxies do not wander randomly through space. Instead, they tend to move along broad pathways shaped by the large-scale structure of the universe. These pathways can be imagined as slow-moving cosmic rivers. In everyday life, rivers form because water flows downhill through landscapes shaped by gravity. Valleys guide the motion of water, while hills and mountains direct its course. The water may twist and branch along the way, but the overall direction is determined by the terrain. Something similar happens on cosmic scales. The terrain of the universe is defined by the distribution of matter, both visible matter and dark matter. Dense regions, such as galaxy clusters, create deep gravitational valleys. Less dense regions form gentle slopes. Voids represent areas where the gravitational landscape is unusually shallow. Galaxies respond to these gravitational contours. Over time, they drift toward the denser structures of the cosmic web, gradually flowing along the filaments that connect clusters and groups. When astronomers plot the velocities of galaxies across large regions of space, they see patterns that resemble currents within an immense river system. The local void plays an important role in shaping these currents near our galaxy. As we discussed earlier, galaxies near the edge of a void tend to move away from its interior because there is very little gravitational pull holding them there. At the same time, dense clusters and filaments located elsewhere exert stronger gravitational attraction. The result is a flow of galaxies away from underdense regions and toward denser ones. When many galaxies participate in this motion simultaneously, the pattern becomes visible on cosmic maps. Astronomers call these patterns large-scale flows. The local group, the collection of galaxies that includes the Milky Way and Andromeda, is part of one such flow. Our galaxy is not simply orbiting within a small local environment, it is also drifting through space as part of a much larger movement involving thousands of galaxies across hundreds of millions of light-years. Mapping these flows has become one of the most fascinating challenges in modern cosmology. To understand how galaxies move through the universe, astronomers must measure not only their positions but also their velocities relative to one another. This requires extremely precise distance measurements and detailed observations of galaxy redshifts. Once these measurements are collected, researchers can construct three-dimensional maps showing how galaxies move relative to the expanding universe. One of the most influential efforts in this area has been the Cosmic Flows project, led by Brent Tully and his collaborators. The project compiles distance measurements for thousands of galaxies, allowing astronomers to reconstruct the velocity field of the nearby universe. When these velocities are visualized, the result is striking. Galaxies appear to stream along filaments like leaves carried along by slow-moving currents. Instead of wandering in random directions, they follow paths shaped by the gravitational structure of the cosmic web. Some of these flows converge toward massive clusters. Others curve around voids, gradually migrating along the boundaries between underdense and overdense regions. In our own cosmic neighbourhood, one of the dominant destinations for these flows is the Virgo cluster. Located roughly 55 million light-years away, Virgo contains thousands of galaxies and enormous amounts of dark matter. Its gravitational influence extends far beyond the cluster itself. Many nearby galaxies, including those in the local group, show signs of drifting in Virgo's general direction. But Virgo is not the only destination guiding these cosmic currents. Beyond Virgo lies an even larger gravitational region, sometimes referred to as the Great Attractor. This structure sits deep within the direction of the Centaurus and Norma clusters. It is partially hidden behind the dense plane of the Milky Way, making it difficult to observe directly. Even so, its gravitational influence is evident in the motion of galaxies across large portions of the nearby universe. Galaxies appear to flow toward that region, as though drawn along a vast gravitational river. At the same time, voids like the local void help shape the pathways of these flows. Because voids contain relatively little mass, galaxies tend to move away from them and toward the denser structures surrounding them. This motion creates a kind of gravitational drainage pattern in which matter gradually migrates toward the nodes and filaments of the cosmic web. In this sense, the cosmic web behaves like a network of rivers feeding into deeper valleys. The local void contributes to the flow by encouraging galaxies near its boundary to drift outward. As galaxies move away from the void, they often join streams of motion that carry them toward nearby filaments and clusters. The Milky Way itself appears to participate in this process. Measurements suggest that our galaxy is moving away from the local void, while simultaneously drifting toward the Virgo cluster and other dense structures farther away. These combined motions form part of the cosmic river carrying our galaxy through the universe. Of course, the word river here is only a metaphor. The actual speeds involved are enormous by human standards, but slow on cosmic scales. Galaxies may move at a few hundred kilometers per second relative to their neighbors, but the distances between them are so vast that it takes billions of years for these motions to produce noticeable changes in their positions. From our perspective on Earth, the night sky appears essentially unchanged over the course of a human lifetime. Yet when astronomers compare galaxy positions across billions of years of cosmic time, the slow currents of the cosmic web become apparent. Simulations of the universe illustrate this behavior beautifully. In computer models that track the evolution of dark matter and galaxies over billions of years, matter gradually flows away from void interiors and accumulates along filaments. Galaxies form within those filaments and then migrate along them toward clusters. The result resembles an intricate network of streams feeding into deeper gravitational basins. One of the most remarkable aspects of these flows is that they connect structures across enormous distances. a galaxy may begin its journey near the edge of a void and slowly drift toward a filament millions of light years away. Over billions of years, it may continue migrating along that filament until it eventually becomes part of a massive cluster. The local group itself may follow such a trajectory. In the distant future, the Milky Way and Andromeda will merge to form a single large galaxy. That new galaxy will likely continue drifting through the cosmic web along the gravitational pathways defined by surrounding structures. Eventually, it may approach larger clusters or become part of a new gravitational grouping formed over billions of years. From our present perspective, however, the journey is only beginning. The local void continues to expand as matter flows outward from its interior. The surrounding filaments grow denser as galaxies accumulate along their lengths. The cosmic rivers of galaxy motion slowly reshape the structure of the universe. Astronomers studying these flows gain valuable insight into the distribution of both visible matter and dark matter. Because galaxy motions respond directly to gravity, they provide clues about the unseen mass that dominates the universe. Even when dark matter cannot be observed directly, its gravitational influence becomes visible through the movement of galaxies. In this way, the cosmic rivers reveal the hidden architecture of the universe. They show where mass is concentrated, where it is scarce, and how matter continues to migrate across vast distances. The local void, despite its emptiness, plays a crucial role in guiding these flows. By creating a region of weak gravitational pull, it encourages galaxies to drift outward and join the currents moving toward denser parts of the cosmic web. Our galaxy's motion through space reflects the combined influence of these enormous structures. Clusters pull us inward, voids allow us to drift outward. Filaments guide the path between them. Together, these elements shape the slow movement of galaxies across the universe. And when astronomers look at the cosmic web as a whole, they see a dynamic system in which matter is constantly flowing, gathering and reshaping the universe's largest structures. Long before astronomers could see the full pattern of the cosmic web, they suspected that something unseen was shaping the universe on the larger scales. When scientists began mapping galaxies in 3 dimensions, the arrangement of those galaxies appeared far too organized to be explained by visible matter alone. Filaments stretched across immense distances, clusters gathered thousands of galaxies into dense knots, and enormous voids opened between them. The structure looked deliberate, almost architectural, as though something invisible had laid down the scaffolding first, and the galaxies simply followed along. That invisible scaffolding is what astronomers call dark matter. Dark matter does not glow, reflect, or absorb light in any measurable way. Telescopes cannot photograph it directly. If you pointed the most powerful optical telescope toward a cloud of dark matter, you would see nothing at all. And yet its gravitational influence reveals that it is everywhere, shaping the motion of galaxies and the structure of the universe. Current estimates suggest that about 85% of the matter in the universe is dark matter. Ordinary matter, the kind that forms stars, planets, gas clouds, and living creatures, accounts for only a small fraction of the cosmic total. Because dark matter interacts primarily through gravity, astronomers must map it indirectly. One of the earliest clues that dark matter existed came from observations of galaxy rotation. When astronomers measured how quickly stars orbit the centers of galaxies, they noticed something puzzling. Stars far from the galactic center were moving much faster than expected. If only visible matter were present, the outer stars should orbit more slowly. The gravitational pull of the galaxy would weaken with distance, causing outer stars to drift more gently around the center. But that was not what astronomers observed. Instead, stars at the edges of galaxies were moving nearly as fast as those close to the center. This suggested that a large amount of unseen mass surrounded each galaxy, providing additional gravitational pull. That unseen mass became known as dark matter. Later observations confirmed that dark matter does not exist only within galaxies. It forms enormous halos surrounding galaxies and clusters, extending far beyond the visible stars. These halos contain far more mass than the galaxies themselves. Over time, astronomers realized that dark matter must also exist on even larger scales. The cosmic web, with its vast filaments and enormous voids, appears to be shaped primarily by the distribution of dark matter across the universe. Galaxies simply form within the densest regions of that invisible framework. If you could somehow see dark matter directly, the universe might look quite different from the familiar star-filled sky we observe today. Instead of isolated galaxies floating through space, you would see a vast network of dark filaments stretching across the cosmos, connecting enormous concentrations of mass. Galaxies would appear as glowing beads scattered along those invisible threads. Mapping that hidden structure is one of the major challenges of modern cosmology. Since dark matter cannot be observed directly, astronomers rely on several clever techniques to reveal where it lies. One of the most powerful methods involves gravitational lensing. Gravity affects not only the motion of objects, but also the path of light. When light from a distant galaxy passes near a massive object, such as a cluster of galaxies, the gravitational field of that mass bends the light's path. This effect acts like a cosmic magnifying glass. Sometimes the distortion is dramatic. A single distant galaxy may appear stretched into arcs or rings as its light passes around a massive cluster. These spectacular images are known as Einstein rings or gravitational arcs. More often, the distortions are subtle. When astronomers analyze images of many distant galaxies, they notice slight patterns in the way their shapes are stretched. These distortions reveal the presence of mass along the line of sight, including dark matter that would otherwise remain invisible. By carefully measuring these distortions across large regions of the sky, scientists can reconstruct maps showing where dark matter must be located. These maps often reveal enormous filaments connecting clusters of galaxies. They also show vast underdense regions corresponding to cosmic voids. In other words, gravitational lensing allows astronomers to trace the invisible skeleton of the cosmic web. Another important technique involves studying the cosmic microwave background, the faint radiation left over from the early universe. This radiation fills all of space and carries tiny variations in temperature that reflect the density fluctuations present shortly after the Big Bang. By analysing these variations with extremely sensitive instruments, scientists can determine how matter was distributed in the early universe. When those early patterns are compared with modern galaxy surveys, the results match remarkably well. Regions that were slightly denser in the early universe eventually grew into clusters and filaments. Regions that were slightly underdense became cosmic voids. The local void itself likely began as a region with slightly less matter than average. Over billions of years, gravity amplified that difference. Matter flowed outward toward neighbouring filaments, gradually enlarging the empty region. Today, the void remains one of the most prominent underdense regions near the Milky Way. Computer simulations provide another powerful way to explore the cosmic web. Researchers use supercomputers to simulate billions of particles representing dark matter and ordinary matter. These particles interact through gravity as the simulated universe expands over billions of years. When the simulation begins, the matter distribution is nearly uniform, containing only tiny fluctuations in density. As time progresses, gravity pulls matter into filaments and clusters, while underdense regions grow into voids. The resulting structure closely resembles the galaxy maps observed by astronomers. Long filaments stretch across hundreds of millions of light years. Clusters appear at the intersections of these filaments. Between them lie enormous empty cavities. When scientists compare these simulations with real observations, they find remarkable agreement. The cosmic web predicted by simulations matches the large-scale structure seen in galaxy surveys. This agreement provides strong evidence that dark matter plays a central role in shaping the universe. Even though we cannot see dark matter directly, its gravitational influence reveals the pattern of its distribution. The local void fits naturally within this framework, Although it contains relatively little matter, its existence reflects the underlying arrangement of dark matter across the cosmic web. The void represents a region where dark matter density is significantly lower than average. Surrounding it are filaments, where dark matter has gathered more densely, providing the gravitational foundation for galaxies to form. In this way, the cosmic web is not simply a pattern traced by galaxies, it is a structure defined primarily by dark matter. Galaxies illuminate the web, but dark matter forms the framework. Understanding that framework helps astronomers explain why the universe looks the way it does. Without dark matter, gravity alone would not have had enough time to form the large-scale structures we observe today. Ordinary matter interacts with radiation in ways that slow down its gravitational collapse in the early universe. Dark matter, by contrast, does not interact strongly with radiation. It was free to begin clumping together much earlier. These early clumps of dark matter eventually grew into the enormous halos and filaments that shaped the cosmic web. Galaxies later formed within those structures as gas cooled and condensed. The local void therefore reflects not only the distribution of galaxies, but also the deeper distribution of dark matter across our region of the universe. Even though the void appears mostly empty, it is part of the larger gravitational landscape created by dark matter. Astronomers continue working to refine maps of this invisible structure. New surveys use increasingly sensitive telescopes to measure gravitational lensing across large areas of the sky. Future missions, including space telescopes designed specifically to study dark matter, will provide even more detailed maps of the cosmic web. These observations may reveal previously unknown filaments and voids, helping scientists understand how matter flows through the universe over billions of years. For now, the cosmic web remains one of the most remarkable discoveries in modern astronomy. It shows that the universe is not a random collection of galaxies scattered through empty space. Instead, it is an intricate network shaped by gravity and the mysterious presence of dark matter. Astronomers first began identifying cosmic voids while mapping the nearby universe, but once galaxy surveys expanded to cover larger and larger portions of the sky, it became clear that the local void was only one example among many. In fact, when researchers looked deeper into the cosmos, they found that enormous empty regions appear throughout the universe, some of them far larger than anything in our immediate neighbourhood. These discoveries came gradually as new surveys charted the positions of millions of galaxies. Each time scientists extended their maps farther into space, the same pattern appeared again and again. Galaxies arranged themselves along long filaments and sheets, leaving behind immense cavities where relatively few galaxies existed. Some of those cavities turned out to be astonishingly large. One of the most famous examples is the Booter's Void, discovered in the early 1980s while astronomers were studying galaxies in the direction of the constellation Boötes. When researchers plotted the positions of galaxies in that region, they noticed a huge spherical area containing almost none. The Boötes Void measures roughly 330 million light-years across. To appreciate the scale of that emptiness, it helps to compare it with familiar cosmic structures. The Milky Way galaxy spans about 100,000 light-years. Even large galaxy clusters like the Virgo cluster stretch across only about 10 million light-years. The Boötes Void is more than 30 times larger than that. If the Milky Way were placed near the centre of the Boötes Void, the nearest major galaxies might lie hundreds of millions of light-years away. The night sky from such a location would look dramatically different from what we see on Earth. Instead of a sky filled with distant galaxies, the surrounding universe would appear unusually sparse. Despite its enormous size, the Boötes Void is not completely empty. Astronomers have discovered a handful of galaxies drifting within it. However, those galaxies are extremely rare compared with typical cosmic environments. In most regions of the universe, galaxies appear every few million light-years. Inside the Boötes Void, the separation between galaxies can be tens of millions of light-years. That discovery was surprising when it first appeared. Until then, astronomers had not fully realized that the universe could contain empty regions of such enormous scale. But the Butter's void was only the beginning. As galaxy surveys expanded during the 1990s and early 2000s, researchers identified many additional voids scattered throughout the cosmic web. Some were smaller, perhaps 20 or 30 million light-years across. Others rivaled the Butter's void in size. In recent years, astronomers have begun cataloguing thousands of cosmic voids using large sky surveys such as the Sloan Digital Sky Survey. These catalogues reveal that voids are extremely common. In fact, they occupy the majority of the universe's volume. Galaxies, clusters, and filaments form the bright outlines of the cosmic web, but the empty regions between them dominate the total space. Some of the largest voids discovered so far stretch hundreds of millions of light-years across. One particularly interesting example is the Eridanus supervoid, an enormous underdense region located in the direction of the constellation Eridanus. This void spans roughly 1 billion light-years across, making it one of the largest known structures of its kind. The Eridanus supervoid attracted attention for another reason as well. Astronomers studying the cosmic microwave background noticed an unusually cold region in the radiation known as the cold spot. Some researchers suggested that the presence of the supervoid might help explain that temperature anomaly. As light from the early universe travels through a large void, the expansion of space can slightly alter its energy. This effect, known as the integrated Sachs-Wolf effect, may contribute to the appearance of cooler or warmer patches in the cosmic microwave background. Although the connection between the Eridanus supervoid and the cold spot remains debated, the idea illustrates how voids can influence observations across enormous distances. Another enormous structure identified in galaxy surveys is the KBC void, named after the astronomers who studied it in detail. Some studies suggest that our galaxy may reside within a large underdense region, extending hundreds of millions of light-years. If that interpretation is correct, the local void we discussed earlier might represent only a smaller cavity within a much larger underdense environment. This possibility remains an active area of research. Measuring the size of extremely large voids is challenging because their boundaries are not sharply defined. Galaxy density gradually increases as one moves outward from the center of a void towards surrounding filaments. Different studies therefore produce slightly different estimates depending on how the boundary is defined. Nevertheless, the existence of extremely large voids appears well established. The largest known examples rival the size of superclusters of galaxies. These enormous structures highlight an important feature of the universe. On the largest scales, the cosmos is not filled uniformly with galaxies. Instead, matter gathers into a network of filaments and clusters separated by vast empty cavities. The local void fits naturally within this pattern. Although it is large compared with many nearby structures, it is not the largest void known. In fact, compared with some of the immense supervoids discovered in distant galaxy surveys, the local void may be considered moderate in size. Its importance comes primarily from its proximity to us. Because the local void sits beside the Milky Way, astronomers can study its effects on nearby galaxies with far greater detail than they can for most other voids. This proximity allows researchers to examine how galaxies move along the edges of a void, how matter flows outward from its interior, and how the void contributes to the large-scale gravitational dynamics of our region of the universe. Even though voids contain relatively little matter, their sheer size means they play a major role in shaping the cosmic web. When multiple voids expand next to one another, their boundaries form the long filaments where galaxies accumulate. These filaments intersect at nodes where galaxy clusters grow. Over billions of years, the combined influence of gravity and cosmic expansion creates the familiar pattern seen in galaxy maps. Voids grow larger, filaments become denser, clusters gather more galaxies. This process continues today. The local void, like other voids across the universe, is slowly expanding as matter flows outward towards surrounding structures. Given enough time, neighbouring voids may merge, forming even larger cavities. Looking far into the future, some cosmologists predict that the universe will eventually become even more dominated by these enormous empty regions. As cosmic expansion accelerates due to dark energy, distant galaxies will gradually drift farther apart. Clusters of galaxies may remain gravitationally bound, but the vast spaces between them will grow larger and emptier. The cosmic web will stretch and thin. From the perspective of future observers living billions of years from now, the universe might appear far more isolated than it does today. Yet for now, the universe remains richly structured, with countless galaxies outlining the filaments between immense voids. The local void represents just one piece of that grand structure, and although it is already enormous by human standards, it may not even represent the largest empty region in our immediate cosmic surroundings. Nothing in the universe begins as a perfect void. Even the emptiest regions we observe today started with matter spread throughout them. To understand why some parts of space eventually became enormous cosmic cavities, it helps to go all the way back to the earliest moments after the Big Bang, when the universe looked very different from the one we see today. During the first few 100,000 years after the Big Bang, the universe was hot, dense, and filled with a glowing mixture of particles and radiation. At that time, matter had not yet gathered into stars or galaxies. Instead, the cosmos resembled a nearly uniform sea of plasma. However, nearly uniform does not mean perfectly uniform. Tiny variations in density existed from the very beginning. Some regions contained slightly more matter than average, while others contained slightly less. These differences were extremely small. Measurements of the cosmic microwave background show that the variations were only about 1 part in 100,000. Yet those tiny fluctuations were enough to shape the entire structure of the universe. Gravity acts on matter wherever it exists. If one region contains slightly more matter than its surroundings, its gravitational pull becomes slightly stronger. Over time, that stronger pull begins attracting additional matter from nearby regions. As matter flows inward, the dense region becomes even denser. At the same time, nearby regions that started slightly less dense begin losing matter. As material flows toward the denser areas, those under dense regions gradually become emptier. This process continues for billions of years. The slightly denser regions eventually form galaxies, galaxy groups, and enormous clusters. Meanwhile, the slightly underdense regions grow into the vast cosmic voids we observe today. In this sense, cosmic voids are not places where matter was removed. They are regions where matter simply migrated away. The early universe provided the starting conditions, and gravity gradually amplified those initial differences. Dark matter played a crucial role in this process. Unlike ordinary matter, dark matter does not interact strongly with radiation. In the early universe, ordinary matter was tightly coupled to radiation through scattering processes. This interaction slowed the collapse of gas clouds, because radiation pressure resisted the gravitational pull trying to compress them. Dark matter behaved differently. Because it interacts primarily through gravity, dark matter was able to begin clumping together earlier than ordinary matter. These early dark matter clumps formed the first gravitational wells in the young universe. Over time, gas fell into those wells and eventually formed the first stars and galaxies. But the same gravitational process also produced the opposite effect in regions where dark matter density started slightly below average. In those regions, matter gradually flowed outward toward neighbouring structures. The result was the formation of large cavities between the growing filaments and clusters. These cavities became cosmic voids. Computer simulations of cosmic evolution illustrate this process beautifully. When researchers simulate billions of particles interacting through gravity, they begin with a nearly uniform distribution containing tiny fluctuations in density. As the simulation evolves, the particles naturally organize themselves into filaments and clusters. At the same time, large empty regions appear between those structures. The pattern that emerges closely resembles the cosmic web observed in galaxy surveys. Filaments stretch across hundreds of millions of light years. Clusters appear at their intersections. Voids fill the spaces between them. The local void is one of these underdense regions formed through the same process. Although it appears enormous today, its origins can be traced back to those tiny density fluctuations present in the early universe. Over billions of years, gravity slowly encouraged matter to migrate away from the region, enlarging the void while strengthening the surrounding filaments. Another important factor in void formation is the expansion of the universe. As space expands, galaxies move farther apart on average. But this expansion does not occur uniformly everywhere. Regions that contain large amounts of matter experience stronger gravitational pull, which slightly slows the expansion of space locally. In contrast, regions with very little matter offer less gravitational resistance. As a result, voids tend to expand slightly faster than denser regions. This effect gradually enlarges the empty cavities within the cosmic web. Imagine drawing a pattern of dots on a balloon and then inflating the balloon. As the balloon expands, the dots move farther apart from one another. But if some regions contain fewer dots than others, those sparse areas will appear even emptier as the balloon grows. The universe behaves in a similar way. As cosmic expansion continues, matter flows away from underdense regions while accumulating along filaments and clusters. This process strengthens the boundaries of the cosmic web while enlarging the voids between them. Voids can also evolve by merging with neighbouring voids. If two underdense regions lie close together, the thin filaments separating them may gradually weaken as matter flows outward towards surrounding structures. Eventually, the barrier between the voids may disappear, allowing the two cavities to merge into a single larger void. This merging process helps explain why some of the largest voids in the universe reach hundreds of millions of light-years across. They may have formed through the gradual combination of many smaller voids over billions of years. The local void itself may connect with nearby underdense regions in this way. Because part of the void lies behind the dusty plain of the Milky Way, astronomers are still refining their maps of the area. Future surveys may reveal that the local void is part of a larger network of connected cavities stretching across a much wider region. Another interesting feature of void formation involves how galaxies behave near the edges of these regions. Galaxies located close to the boundaries of a void tend to drift outward over time. This happens because the gravitational pull from surrounding filaments is stronger than the weak gravitational influence of the void interior. As galaxies move outward, they accumulate along the boundaries between neighbouring voids. These boundaries eventually become the filaments and walls of galaxies that define the cosmic web. In this way, voids help shape the large-scale structure of the universe. Without them, the cosmic web would not exist in its familiar form. The interplay between void expansion and filament formation creates the complex pattern astronomers observe in galaxy surveys. The local void provides a nearby example of this process. Its interior contains relatively few galaxies because most of the matter originally present there has gradually migrated outward over billions of years. The surrounding regions where matter has accumulated now contain galaxy groups and filaments that outline the edges of the void. Even though the void appears empty today, its formation reflects the same gravitational forces that built galaxies and clusters elsewhere in the universe. Voids are therefore not anomalies. They are a natural consequence of how gravity organises matter across cosmic time. Understanding this process helps astronomers answer deeper questions about the universe. By studying the size and distribution of voids, scientists can test theories about dark matter, cosmic expansion, and the growth of structure over billions of years. Voids act as sensitive probes of cosmology because their shapes and sizes depend on the underlying physics governing the universe. The local void, despite its quiet appearance, plays an important role in this research. Because it lies so close to our galaxy, astronomers can observe its effects on nearby galaxies with exceptional detail. These observations help refine our understanding of how matter flows through the cosmic web and how voids evolve over time. Billions of years from now, the universe will not look exactly the way it does today. The night sky above Earth already feels steady and familiar because the motions of galaxies unfold so slowly that they barely change over a human lifetime. Yet on cosmic timescales, the structure of the universe is constantly evolving. Galaxies drift, clusters grow, and voids gradually expand as matter continues to migrate through the cosmic web. The local void is part of that slow transformation. At the present moment, the local void is already a vast underdense region beside our galactic neighbourhood. Galaxies exist within it, but they are few and extremely far apart. Most of the matter that once occupied this region has already migrated towards surrounding filaments and galaxy groups. As the universe ages, this process will continue. One of the main reasons is the ongoing expansion of space itself. Since the Big Bang, the universe has been expanding in all directions. Galaxies that are not gravitationally bound to one another gradually move farther apart as the fabric of space stretches. This expansion affects all regions of the universe, but it has a particularly strong influence inside cosmic voids. Because voids contain relatively little matter, there is very little gravitational pull opposing the expansion of space within them. In dense regions such as galaxy clusters, gravity partially counters cosmic expansion by holding galaxies together. Inside a void, that resistance is much weaker. As a result, voids tend to grow larger over time. The local void is already expanding slowly as galaxies near its boundaries drift outward toward denser regions of the cosmic web. Over billions of years, this outward motion will gradually enlarge the empty region. The galaxies currently living inside the void may eventually move closer to its edges, joining the filaments where matter continues to accumulate. Computer simulations of cosmic evolution show that this pattern repeats across the universe. When scientists simulate the growth of cosmic structure over billions of years, voids steadily expand, while filaments become thinner and more pronounced. The cosmic web slowly stretches, with empty regions occupying an ever larger fraction of space. The local void is expected to follow the same path. Over the next several billion years, the structure of our nearby universe will also change in other ways. One of the most dramatic events will involve the Milky Way and the Andromeda galaxy. These two galaxies, currently separated by about 2.5 million light-years, are moving slowly toward each other due to their mutual gravitational attraction. In roughly 4 to 5 billion years, they are expected to collide and merge. The merger will produce a new, much larger galaxy, sometimes referred to by astronomers as Milky Way. Although the event will dramatically reshape the structure of both galaxies, the vast distances between individual stars mean that actual stellar collisions will be extremely rare. After the merger, the new galaxy will continue drifting through the cosmic web, influenced by the same gravitational forces that affect the Milky Way today. The local void will still be there. In fact, by that time it may have grown even larger. The continued expansion of the universe will gradually push distant galaxies farther away from our region of space. Many galaxies that are currently visible in large telescopes will eventually drift beyond our cosmic horizon. This effect is caused by dark energy, the mysterious phenomenon driving the accelerated expansion of the universe. Dark energy causes the expansion of space to increase over time. As a result, galaxies that are not gravitationally bound to our local region will eventually recede faster than light can travel across the expanding space between us. When that happens, their light will no longer be able to reach us. From the perspective of future observers living billions of years from now, the observable universe may look very different. Most distant galaxies may no longer be visible. The sky may contain only the remnants of our local group of galaxies, along with the merged galaxy formed from the Milky Way and Andromeda. Beyond that, enormous stretches of space may appear almost completely empty. In that distant future, the local void will likely dominate much of the cosmic landscape visible from our region. Without the distant galaxies currently outlining the cosmic web, the surrounding universe may appear far more isolated. The filaments that now connect galaxy clusters across hundreds of millions of light-years will still exist, but many of the galaxies that once illuminated them will have moved beyond the observable horizon. Voids will appear even larger from the perspective of observers inside a gravitationally bound galaxy group. Over extremely long timescales, this isolation will become more pronounced. The local void will continue expanding as matter slowly migrates outward from its interior. Neighbouring voids may merge with it, creating even larger cavities within the cosmic web. Eventually, the structure of the universe may resemble an enormous collection of isolated islands of galaxies, separated by vast regions of emptiness. Our merged galaxy may become one such island. Of course, these changes occur over timescales far beyond human history. Even over the next billion years, the local void will appear almost unchanged from our perspective. The motions involved are so gradual that the cosmic landscape evolves only slowly. But given enough time, the quiet expansion of voids will reshape the universe. The cosmic web will stretch, filaments will thin, and empty regions will dominate more and more of the cosmic volume. From a certain point of view, the local void offers a glimpse of what the far future of the universe may look like. A place where galaxies are rare, where distances between structures grow immense, and where the night sky becomes increasingly quiet. Yet even in that distant future, the underlying structure of the universe will still reflect the same physical processes that shaped it from the beginning. Gravity will continue guiding matter along the remaining filaments. Dark matter will still form the invisible framework holding galaxies together, and cosmic expansion will keep stretching the universe, gradually enlarging the spaces between structures. The local void will not remain static, but its slow growth will be part of the ongoing evolution of the cosmic web. And as astronomers continue studying this nearby void today, they gain insight not only into the structure of our present universe, but also into the distant future that awaits it. Standing inside a galaxy, it is easy to imagine that the universe is filled everywhere with stars, galaxies, and glowing clouds of gas. When we look up at the night sky from Earth, even with the naked eye, the sky appears crowded. Thousands of stars are visible, and telescopes reveal countless distant galaxies beyond them. From this perspective, the universe seems richly populated, yet the true structure of the cosmos tells a different story. Most of the universe, by volume, is not filled with galaxies at all. Instead, it consists of vast regions where matter is extremely sparse. Cosmic voids dominate the overall volume of space, while galaxies occupy only the thin filaments and clusters outlining the edges of these enormous cavities. Our own galaxy happens to sit in a particularly interesting location within this structure. The Milky Way is not located deep inside a dense galaxy cluster, nor does it reside at the centre of a vast cosmic void. Instead, it lies near the boundary between two very different environments, a region containing the galaxies of our local cosmic neighbourhood and the enormous emptiness of the local void. In a sense, we live on the shoreline of one of the universe's largest deserts. This position may sound dramatic, but it also has subtle consequences for how our galaxy experiences the universe around it. To understand what it means to live near the edge of a cosmic void, it helps to think about the structure of the cosmic web once again. On the larger scales, matter in the universe forms a network of filaments stretching across hundreds of millions of light years. These filaments intersect at nodes where galaxy clusters gather. Between them lie enormous voids where relatively little matter exists. Galaxies tend to accumulate along the filaments because gravity pulls matter toward these dense structures. Voids represent the opposite situation. They are regions where matter density is far below average. The local void is one of these regions, and our galaxy sits close to its boundary. Because of this location, the Milky Way experiences the gravitational influence of two different environments simultaneously. On one side lies the relative emptiness of the void. On the other side lie the filaments and galaxy groups that form the nearby structure of the universe. The gravitational pull from these denser regions slightly outweighs the influence of the empty space behind us. Over billions of years, this imbalance contributes to the motion of our galaxy away from the void and toward nearby structures. But beyond its effect on galaxy motion, living near the edge of a void also shapes our cosmic surroundings in other ways. For one thing, the distribution of nearby galaxies reflects this boundary. When astronomers map the positions of galaxies around the Milky Way, they find that our galaxy belongs to a modest gathering known as the local group. This group contains about 50 known galaxies, including the Milky Way, the Andromeda Galaxy, and several dozen smaller dwarf galaxies. The local group itself is not part of a dense galaxy cluster. Instead, it resides within a filament of the cosmic web that stretches between larger structures. One side of this filament borders the local void, while the other connects to regions containing additional galaxy groups. This means that when astronomers look outward from our galaxy in certain directions, they encounter relatively rich structures filled with galaxies. When they look in other directions, they find much less. The local void lies in one of those directions where the number of nearby galaxies drops dramatically. From a cosmic perspective, our galaxy sits along the wall of a large empty bubble. Living on the boundary of a void also means that our cosmic neighbourhood is relatively calm compared with more crowded parts of the universe. Galaxy clusters can contain thousands of galaxies packed within relatively small volumes. In such environments, galaxies frequently interact with one another through gravity. Close encounters can distort their shapes, strip gas from their disks, and trigger bursts of star formation. In extreme cases, galaxies may collide and merge repeatedly within clusters. The local group is far quieter. Although the Milky Way and Andromeda will eventually collide billions of years from now, interactions within our group occur far less frequently than in dense clusters. Part of this quiet environment may be related to our location near the boundary of the local void. Because the surrounding region contains fewer galaxies overall, the likelihood of frequent gravitational encounters is reduced. This calmer environment may have had important consequences for the history of our galaxy. The Milky Way has certainly experienced mergers with smaller galaxies in the past, but its overall structure remains relatively stable compared with many galaxies found in dense clusters. Some astronomers have suggested that living near the edge of a void might even influence the long-term evolution of galaxies. In regions where galaxies are less crowded, gas can remain available for star formation over longer periods of time. Galaxies may evolve more gradually rather than undergoing repeated bursts of activity triggered by collisions. This idea remains an active topic of research. Another interesting consequence of living near the edge of a void involves the large-scale flows of galaxies we discussed earlier. Because the local void contains relatively little matter, galaxies near its boundary tend to drift away from its interior over time. This motion contributes to the broader cosmic flows that guide galaxies along filaments toward dense clusters. The Milky Way participates in these flows as part of the local group. Our galaxy's motion through space reflects the combined influence of nearby clusters, large-scale filaments, and the underdense region of the local void behind us. From a human perspective, however, these motions are almost impossible to notice. Even though our galaxy moves through space at hundreds of kilometers per second, the distances between galaxies are so vast that the sky appears essentially unchanged over the course of human history. Stars rise and set. Constellations slowly shift over tens of thousands of years, but the broader cosmic landscape remains steady on timescales relevant to human life. Yet astronomers studying the universe across billions of years can see the subtle changes unfolding. Galaxies gradually drift along the filaments of the cosmic web. Voids slowly expand as matter flows outward. Clusters grow as galaxies accumulate within them. Our galaxy's position along the edge of the local void offers scientists a unique vantage point for observing these processes. Because the void lies so close to us, astronomers can measure the motions of nearby galaxies with great precision. By studying how galaxies move relative to the void, researchers gain insight into how under-dense regions influence the gravitational dynamics of the cosmic web. The local void therefore acts as a nearby laboratory for understanding how the universe organises itself on the larger scales. It reminds us that emptiness can be just as important as matter when shaping the structure of the cosmos. From our perspective inside the Milky Way, the local void may seem remote and abstract. After all, even the closest parts of it lie tens of millions of light years away. No spacecraft will ever travel there, and no human observer will witness its slow expansion directly. Yet its presence still influences the environment in which our galaxy exists. The local void helps shape the gravitational landscape guiding the motion of galaxies across our region of the universe. It forms part of the enormous network of cavities and filaments that define the cosmic web, and it reminds us that the universe is structured not only by what is present, but also by what is absent. Our galaxy happens to live on the boundary between those two realities. Behind us lies one of the largest empty regions in our cosmic neighbourhood. Ahead of us lie the filaments and clusters where galaxies gather. From this quiet edge between structure and emptiness, astronomers continue mapping the universe, slowly uncovering the immense patterns that connect galaxies across billions of light years. And as they do, the local void stands as a reminder that even the quietest regions of the cosmos play an important role in shaping the universe we inhabit. Step outside on a clear night and look upward for a moment. The sky appears full, stars fill the darkness, and with the help of telescopes we know that countless galaxies exist far beyond what the human eye can see. At first glance, the universe seems crowded with light. But the deeper astronomers look into space, the more they realise that most of the universe is not crowded at all. Most of it is empty. Galaxies gather along thin filaments that stretch across unimaginable distances, forming the cosmic web that defines the large-scale structure of the universe. Between those filaments lie enormous cavities, regions where matter is scarce and galaxies become rare. These regions dominate the volume of the cosmos, and one of them sits right next to us. Throughout this exploration, we have been looking at a place known as the local void. It is not a distant curiosity located hundreds of millions of light years away. Instead, it lies directly beside the Milky Way, beginning just beyond the boundary of our cosmic neighbourhood. The Milky Way, along with the other galaxies of the local group, occupies the edge of this enormous region. From our position here on Earth, the local void is invisible in the ordinary sense. It does not glow and it does not cast shadows across the sky. There is no dark patch among the stars that marks the beginning of its boundary. Yet its presence is real. Astronomers see its influence in the distribution of galaxies around us. In certain directions, galaxies become less common. In others, they gather along the filaments and clusters that outline the cosmic web. When scientists map those galaxies in 3 dimensions, a vast cavity appears beside our region of space, the local void. It is difficult to fully appreciate the scale of something so large. The void may stretch roughly 150 million light years across, perhaps more depending on how its boundaries are defined. Within that enormous volume, galaxies are extremely rare. If the Milky Way were placed deep inside the centre of such a region, the nearest galaxies might lie tens of millions of light years away. The night sky in that location would look dramatically different from the one we see on Earth. Instead of countless distant galaxies shining faintly in deep telescope images, the surrounding universe might appear strangely quiet. Yet even in this emptiness, the local void is not completely devoid of structure. A few galaxies drift quietly through its interior. They are isolated, separated by enormous distances from their nearest neighbours. Their slow evolution offers astronomers valuable insight into how galaxies develop when left largely undisturbed. The void also influences the motion of galaxies around its edges. Our own galaxy participates in that motion. The Milky Way and its neighbouring galaxies appear to be drifting away from the interior of the local void, gradually migrating toward denser structures such as the Virgo cluster and other filaments of the cosmic web. This movement unfolds incredibly slowly. Even travelling at hundreds of kilometres per second, galaxies take millions of years to move distances that are noticeable on cosmic scales. Over billions of years, however, these subtle motions reshape the structure of the universe. Matter flows outward from underdense regions, voids grow larger, filaments become more pronounced. The cosmic web evolves. The local void participates in this ongoing transformation. Although it may appear static from our human perspective, the void is slowly expanding as matter continues migrating towards surrounding structures. Over immense stretches of time, neighbouring voids may merge with it, creating even larger regions of cosmic emptiness. At the same time, the galaxies along its boundaries continue their slow journeys through space. Our own galaxy is part of that journey. The Milky Way is not sitting still within the universe. It is moving along with the local group, drifting through the gravitational landscape shaped by both matter and emptiness. Clusters of galaxies pull us in one direction. Voids encourage motion in another. The result is a slow cosmic voyage across millions of light years. From our perspective here on Earth, this motion is almost impossible to notice. The stars above us appear fixed in place, forming patterns that have remained recognizable throughout recorded human history. Even the nearest galaxies seem unmoving against the distant background of the cosmos. Yet the universe itself is dynamic. Galaxies drift, clusters grow, and voids expand as gravity and cosmic expansion shape the structure of space. The local void is one quiet example of that process. It reminds us that the universe is not simply a collection of galaxies scattered randomly through space. Instead, it is an intricate structure built over billions of years by the interplay of gravity, dark matter, and cosmic expansion. The luminous galaxies we observe are only the bright outlines of a much larger architecture. Most of the universe lies in the vast spaces between them. From a certain perspective, that emptiness can feel unsettling. Humans tend to focus on the things we can see: stars, planets, galaxies. The idea that most of the universe consists of enormous regions containing very little matter can seem strange. But these empty regions are not meaningless gaps. They play a vital role in shaping the cosmic web. Without voids, the universe would look very different. Matter would not flow along filaments or gather into clusters in the same way. The large-scale structure of the cosmos depends on the presence of both dense regions and empty ones. Voids and clusters are two sides of the same cosmic process, and the local void happens to be one of the nearest examples we can study. Its proximity gives astronomers an opportunity to observe how galaxies move along the boundaries of a void, how matter flows outward from underdense regions, and how the cosmic web evolves over time. These observations help refine our understanding of the universe on its larger scales. Yet the local void also invites a quieter reflection. Right beside our galaxy lies an enormous region of space, where galaxies are rare and distances stretch for tens of millions of light years in every direction. It is a reminder that the universe is far larger and more varied than the small portion we see in the night sky. Even the vast structures revealed by our most powerful telescopes represent only a small part of the cosmos. Beyond them lie countless other voids, filaments, and clusters stretching across billions of light years. The local void is simply the nearest example of that immense cosmic architecture, and perhaps that is what makes it so fascinating. Because just beyond the familiar structures of our galactic neighbourhood, there is a quiet region of space where the universe opens into extraordinary emptiness, a vast cosmic bubble sitting quietly beside the Milky Way, a place where galaxies become rare and the distances between them grow immense, a reminder that even in the deepest darkness of space, the structure of the universe continues to unfold across scales that challenge our imagination. And as astronomers continue mapping the nearby cosmos, studying galaxy motions and refining their measurements of the local void, our understanding of this quiet neighbour will continue to grow. The empty region next door may appear calm and unchanging, but it remains part of the dynamic universe that surrounds us. And tonight, as the Earth rotates quietly beneath the stars, our galaxy continues its slow journey along the edge of that vast cosmic emptiness,